Book in Literature Degree Holder Association, Dharwad. Sir published more than 20 books and 50 articles is published. He recorded lyrics to the Lahiri Recording Company, Bangalore, like Preetiya Inchara, Nanna Manada Kogile and Deepamali. Sir recognition award like Karnataka Rajyotsava Award by the Hubli Dharwad Municipal Corporation in the year 1919. Guided more than 10 students for the award of PhD and 9 students for the award of MPhil. And with this, I welcome Professor Matya sir to this function.
Thank you, madam. May I now respectfully request our esteemed dignitaries to graciously unveil the abstract book. This publication reflects the collective scholarly efforts and intellectual contributions presented at this symposium. Please kindly proceed with the release. Thank you, everyone. Gratitude is the fairest blossom which springs from soul. To express our heartfelt appreciation, we would now like to felicitate our respected guest. I request Professor M.M. Shikare sir to receive this token of love and respect. I request all the dignitaries to join the stage for felicitation. Thank you. Now I request Professor I.G. Sandhi sir to receive this token of love and respect.
Thank you, sir. There is a quote: words have the power to inspire, uplift, and transform. And today we are blessed to have a personality whose words inspire. Let's welcome Professor H.B. Walikar, sir, to address the gathering.
ಪ್ರೊಫೆಸರ್ ಸಿಕ್ಕಾರೆ ಅವರೇ, ಅಧ್ಯಕ್ಷತೆಯನ್ನು ವಹಿಸಿದ ಪ್ರೊಫೆಸರ್ ಮಠ್ಯಾಳ್ರವರೇ ಹಾಗೂ ನನ್ನ ವೇದಿಕೆಯ ಮೇಲಿನ ನನ್ನ ಅಭಿಮಾನಿ ಬಳಗವೇ ಮತ್ತು ವೇದಿಕೆ ಕೆಳಗಿನ ಎಲ್ಲ ಹಿರಿಯರೇ ಹಾಗೂ ಗಣ್ಯರೇ, ನಾನಿಲ್ಲಿ ಒಂದು ಮಾತು ಹೇಳಲೇಬೇಕು. ಏನಂದ್ರೆ, ನಾನು ಇಲ್ಲಿ ನಿಂತಿದ್ದಕ್ಕೆ ಕಾರಣ, ಇಲ್ಲಿ ನಿಂತು ಮಾತನಾಡಲಿಕ್ಕೆ ಕಾರಣ, ವಿಶ್ವವಿದ್ಯಾಲಯದಲ್ಲಿ ಅಧ್ಯಾಪಕನಾಗಲಿಕ್ಕೆ ಕಾರಣ, ಕುಲಪತಿ ಆಗಲಿಕ್ಕೆ ಕಾರಣ, ನನ್ನ ಎಲ್ಲ ಹಂತಗಳಲ್ಲಿ ಮೂಲ ಬೀಜವನ್ನು ಬಿತ್ತಿದವರು ಪ್ರೊಫೆಸರ್ I.G. ಸಂಧಿ ಅವರು. ಯಾಕೆ ಹೇಳ್ತೀನಿ ನಾನು ನಿಮಗೆ, ಅದೇ MA ಮುಗಿದಿತ್ತು 76ರಲ್ಲಿ. ನನಗೆ UGC ರಿಸರ್ಚ್ ಫೆಲೋಶಿಪ್ ಸಿಕ್ಕಿತ್ತು. ಸಿಕ್ಕುಳ್ಳೇ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಡಿಪಾರ್ಟ್ಮೆಂಟ್ನೊಳಗೆ ನನಗೆ ಯಾರಿಗೂ ಗೈಡ್ ಮಾಡಲಿಕ್ಕೆ ತಯಾರಿದ್ದಿಲ್ಲ. ಅದು ಹಿರಿಯರು ತಪ್ಪು ತಿಳ್ಕೊಬಾರ್ದು, ಯಾರಿಗೂ ತಯಾರಿದ್ದಿಲ್ಲ. ಆಗಿನ ಕಾಲನೇ ಬೇರೆ ಇತ್ತು. ಏನಿತ್ತು ಅಂದ್ರೆ, ಈ ಗೈಡ್ಸ್ ಅಂದ್ರೆ ಚಕ್ರಾಧಿಪತಿಗಳು. ಅವ್ರು ತೊಗೊಂಡ್ರೆ ಬಂಟು, ತೊಗೊಳ್ಳಿಲ್ಲ ಅಂದ್ರೆ ಇಲ್ಲ. ಆ ಥರ ವಾತಾವರಣ ಆಗಿನ ಕಾಲದಲ್ಲಿ ಇತ್ತು. ಆವಾಗ ನನಗೆ UGC ಫೆಲೋಶಿಪ್ ಬಂದ ಕೂಡಲೇ ನನಗೆ ಅತಿ ಆತ್ಮೀಯರಾದಂಥ ಒಬ್ಬ MLC ಹಿರಿಯರು ಹುಬ್ಬಳ್ಳಿಯಲ್ಲಿ ಕಲ್ಲಣ್ಣವರಂತ NN ಕಲ್ಲಣ್ಣವರ ಅವ್ರ ಮನೆಗೆ ಹೋಗಿ, ಸರ್ ನನಗೆ ಹಿಂಗೆ UGC ಫೆಲೋಶಿಪ್ ಸಿಕ್ಕದ, ನನಗೆ ಮಾಡಂಗಾರೆ UGC. ಅವರು ಅಗದಿ ಪಕ್ಷಪಾತಿ. ಅವರು ಸರ್ ಸಿದ್ದಪ್ಪ ಕಂಬಳಿಯವರ ಶಿಷ್ಯರು. ಅವರು NN ಕಲ್ಲಣ್ಣವರು ವಿದ್ಯಾಪಕ್ಷಪಾತಿ. ಹೌದಾ, PhD ಮಾಡಂಗಾರ, ಸ್ಕಾಲರ್ಶಿಪ್ ಸಿಕ್ಕದಂದ್ರೆ ನನಗೆ ಭಾಳ ಖುಷಿ ಆಯ್ತಲ್ಲೋ ಅಂದರು. ಅಂದ ಕೂಡಲೇ ಸರ್ ನನಗೆ ಗೈಡ್ ಯಾರೂ ಇಲ್ಲ. ಹೌದಾ, ತಡಿಯಲ್ಲಿ ಅಂತ ಪ್ರೊಫೆಸರ್ ಐ ಜಿ ಸಂಧಿ ಅವ್ರಿಗೆ ಫೋನ್ ಮಾಡಿದರು. ಅವ್ರು ಕಾರ್ ತೊಗೊಂಡು ಬಂದು ಕಲ್ಲಣ್ಣವರು, ನಾನು ಮತ್ತು ಪ್ರೊಫೆಸರ್ ಐ ಜಿ ಸಂಧಿ ಅವರು ಪ್ರಥಮವಾಗಿ ಪ್ರೀಮಿಯರ್ ಪದ್ಮಿನಿ ಕಾರ್ ಇದ್ದಂಗಿತ್ತು ಅವ್ರದ್ದು. ಬಹುಶಃ ಆವಾಗ ನಾ ಕಾರಿನಲ್ಲಿ ಹತ್ತಿದ್ದೆ ಐ ಜಿ ಸನ್ನಿಧಿ ಅವ್ರ ಕಾರ್ ಫಸ್ಟ್. ಅವರು ಕರ್ಕೊಂಡು ಬಂದು ಆರ್ ಸಿ ಹಿರೇಮಠರ ಮನೆಗೆ ಬಂದರು. ಹೀಗೆ ಅಂತ ಅವರು ಖುಷಿಯಿಂದ ಪಿ ಎಚ್ ಡಿ ಮಾಡಲ್ಲ, ನಾನು ಸ್ಕಾಲರ್ಶಿಪ್ ಕೊಡಿಸ್ತೀನಿ ಅಂದ್ರೆ ಆರ್ ಸಿ ಹಿರೇಮಠರು. ನನಗೆ ಸ್ಕಾಲರ್ಶಿಪ್ ಸಿಕ್ಕದು ಸರ್, ಅದರ ಗೈಡ್ ಇಲ್ಲ. ಯಾರ ಕಡೆ ಮಾಡ್ಬೇಕಂತ ಮಾಡಿ, ನಾನು ಸಂಪತ್ ಕುಮಾರ್ ಸರ್ ಕಡೆ ಮಾಡ್ಬೇಕಂತ ಮಾಡಿ. ಯಾಕಂದ್ರೆ ಅವರು ಅತ್ಯುತ್ತಮ ಸಂಶೋಧಕರು. ಅವರನ್ನೇ ನಾನು ಮನಸ್ಸಿನಲ್ಲಿ ಇಟ್ಕೊಂಡು ಅವ್ರಿಗೆ ಹೇಳಿದೆ. ಹೌದಾ ತಡಿಯಲ್ಲಿ ಅಂತ ಫೋನ್ ತೊಗೊಂಡೇ ಬಿಟ್ರು. ಸಂಪತ್ ಕುಮಾರ್ ಅವರೇ, ನಾನು ಒಬ್ಬ ಹುಡುಗನ ಕಳಿಸ್ತೀನಿ, ಅವ್ರನ್ನ ರಿಜಿಸ್ಟ್ರೇಷನ್ ಮಾಡಿಸ್ಕೊಂಬಿಡ್ರಿ, ಕಳಿಸಿ ಸಾರ್. ಸಂಪತ್ ಕುಮಾರ್ ಸರ್ಗೆ ಸಿಟ್ಟು ಬಂದಿತ್ತು. ನಾವು ಹೋದೆ. ಏನು ವಸೀಲಿ ಹೆಚ್ಚು ಪಿ ಎಚ್ ಡಿ ಮಾಡ್ತೇನೆ ನೀನಂದ್ರು. ಅಂದ್ಕೊಳ್ಳೆ ನಾನು ಸುಮ್ಮನೆ ಆದೆ. ಮುಂದೆ ಅವ್ರಿಗೆ ಮನಸ್ಸಿನೊಳಗೆ ಏನಿತ್ತೋ ಗೊತ್ತಿಲ್ಲ, ಈ ಮನುಷ್ಯ ವಸೀಲಿ ಮೇಲೆ ಬಂದಾನ ಅಂತ ತಿಳ್ಕೊಂಡು ನನಗೆ ಕೇರೆ ಮಾಡ್ತಿದ್ದಿಲ್ಲ. ಮುಂದೆ ನಾನು ಲೈಬ್ರರಿಯಲ್ಲಿ ಕೂತ್ಕೊಂಡು ಒಂದು ರಿಸರ್ಚ್ ಪೇಪರ್ ಬರೆದೇ ಬಿಟ್ಟೆ. ನಾನು ಒಂದು 6 ತಿಂಗಳದೊಳಗೆ ತೊಗೊಂಡು ಹೋಗಿ ತೋರಿಸಿದೆ. ನಾನು ಸುಟ್ಟಿತ್ತು ಅವ್ರು ನನ್ನ ಮೇಲೆ. ಏನು ಮಾಡಿ? ಏನೋ ಮಾಡೀನಿ ಸರ್, ನೋಡ್ರಿ ಅಲ್ಲಿಟ್ಟೋಗು ಅಂದರು. ಇಟ್ಟು ಬಂದೆ. ಮತ್ತು ಲೈಬ್ರರಿಯಲ್ಲಿ ಕೂತಿದ್ದೆ. 4-5 ದಿನ ಆದ ಮೇಲೆ ಒಬ್ಬ ನನ್ನ ಸಹೋದ್ಯೋಗಿಯನ್ನು ಅಂದರೆ ರಿಸರ್ಚ್ ಸಹೋದ್ಯೋಗಿ ಕಳಿಸಿದರು. ಕರ್ಕೊಂಡು ಬಾ ವಾಲಿಕಾರ್ನಂದರು. ಹೋದೆ. ಅಂತೂ ಮಾಡ್ತೀವಿ ಬಿಡು ನೀನು, ನಾನು ಗ್ರಾಮರ್ ತಪ್ಪದವ ನಾನು ತಿದ್ದೀನಿ, ಟೈಪ್ ಮಾಡಿಸಿ ಜರ್ನಲಿಗೆ ಕಳಿಸ್ಬಿಡು ಅಂದರು. ಆವಾಗ ನನಗೆ ಓದು ಜೀವ ಬಂದಂಗೆ ಆಯಿತು. ಮುಂದೆ ನನಗೆ ಆಶ್ಚರ್ಯ ಅಂದ್ರೆ ಅವರು ವಿದೇಶಕ್ಕೆ ಹೋದರು. ನಾನು ಒಂಥರ ಒಂಟಿ ಸಲಗನಂತೆ ನಾನು ಒಬ್ಬನೇ ನನಗೇನು ತಿಳಿತದ ಅದನ್ನು ಮಾಡಿ ಅವ್ರಿಗೆ ಬರೆದು ಕಳಿಸ್ತಿದ್ದೆ. ಅವರು ಖುಷಿಯಿಂದ ನೋಡಿ ಮತ್ತು ಜರ್ನಲಿಗೂ ಸಬ್ಮಿಟ್ ಮಾಡಿಬಿಡ್ತಿದ್ದೆ. ಆ ಕಾಪಿ ಅವ್ರಿಗೆ ಕಳಿಸ್ತಿದ್ದೆ. ಬಹಳ ಖುಷಿಯಿಂದ ಪತ್ರ ಬರೋರು. ನಾನು ಈ ಸ್ಟೂಡೆಂಟ್ ಒಳಗೆ ನೀನು ನನಗೆ ಭಾಳ ಖುಷಿ ತಂದೀಯಪ್ಪ, ನನಗೆ ಭಾಳ ಖುಷಿಯಾಗೈತೆ, ಇನ್ನೂ ಮುಂದುವರಿ ಅಂತ ಬೆನ್ನು ಚಪ್ಪರಿಸ್ತಿದ್ರು. ಎಲ್ಲೇ ಕಾನ್ಫರೆನ್ಸ್ಗೆ ಹೋದರೂ ನನ್ನ ಕೈ ಹಿಡ್ತಿದ್ರು. ಆ ನೇರ್ಲಿಗೆ ಮೇಡಮ್ ಅವ್ರಿಗೆ ಗೊತ್ತದು. ಅಂಥ ಮನುಷ್ಯ ಬಹಳ ಪ್ರೀತಿ. ದುರ್ದೈವದಿಂದ ನಮ್ಮ ನಡುವೆ ಈಗಿಲ್ಲ ಅವರು. ಅವರ ಪ್ರೀತಿ ಪ್ರೋತ್ಸಾಹ ಕಾರಣಕ್ಕೆ ನನ್ನ 3ನೇ ಮಗನಿಗೆ ಅವ್ರ ಹೆಸರೇ ಇಟ್ಟಿದ್ದೀನಿ, ಸಂಪತ್ ಕುಮಾರ್ ಅಂತ. ಆಮೇಲೆ ಇನ್ನೊಂದು ಮಾತು ಹೇಳಿ ನಾನು ಮುಗಿಸ್ಬಿಡ್ತೀನಿ. ಭಾಳ ಹೇಳೋದು ಬೇಡ. ನನ್ನ ವೈಯಕ್ತಿಕ ಜೀವನದ ಸಂಗತಿಯನ್ನು ನಿಮ್ಮ ಮುಂದಿಟ್ಟೆ. ಪ್ರತಿ ಹಂತದಲ್ಲೂ ನಾನು ಇಲ್ಲಿ ಹೊಡೆದಾಡೇ ಬಂದಿದ್ದೀನಿ. ಇಲ್ಲೇ ಕರ್ನಾಟಕ ವಿಶ್ವವಿದ್ಯಾಲಯದಲ್ಲಿ ಬರಬೇಕಾದ್ರೆ ಪ್ರತಿ ಹಂತದಲ್ಲಿ ಹೋರಾಟ ನಂದು. ಹೀಗಾಗಿ ಅದು ಏನೋ ನನಗೆ ಗೊತ್ತಿಲ್ಲ, ಆ ಛಲ ನನ್ನಲ್ಲಿತ್ತು. ಬಿಡಬಾರ್ದು ಅನ್ನುವಂಥ ಛಲ ಇತ್ತು. ಆ ಛಲನೇ ನನ್ನನ್ನು ವಿಶ್ವವಿದ್ಯಾಲಯದ ಉನ್ನತ ಹುದ್ದೆಗೆ ಒಯ್ಯಿತು ಅಂತ ನನ್ನ ಭಾವನೆ. ಹಾಗೆ ಇನ್ನು ಒಂದೇ ಒಂದು ಮಾತು ಹೇಳ್ತೀನಿ ನಾನು. ಭಾಳ ಹೇಳೋದಿಲ್ಲ ಅಂತ ಇಟತ್ತನ ಹೇಳಿದ್ದೇನು. ಒಂದು ನಮ್ಮ ನಾಟಿಕರವ್ರು ಹೇಳಿದರು, ಇವತ್ತು ಎಂಗೇಜ್ಮೆಂಟು ನಾಳೆಗೆ ಮದುವೆ ಅಂತ. ಅದು ನನ್ನ ಮೊಮ್ಮಗಳು ಕೇಳಿದ್ದು. ಒಮ್ಮೆ 25ನೇ ಮದುವೆ ಇದ್ರಾಗ ಒಮ್ಮೆ ಆಯಿತು. ಆಮೇಲೆ 60ನೇ ವರ್ಷದಾಗ ಇಲ್ಲಿ ಇದೇ ಸಭಾಭವನದಲ್ಲಿ ಹಾರ ಹಾಕಿದೆ. ಆಕೆನೂ ನನಗೆ ಹಾರ ಹಾಕಿದ್ಲು. ಅಜ್ಜಿ ನೀ ಎಷ್ಟು ಸಲ ಮದುವೆ ಆಗ್ತೀವಿ ಅಂತ ಕೇಳಿಲ್ಲ. ಕೇಳಿದ ಕೂಡಲೇ ನಾನು ಅಂದೆ, ಏನವ ಎಷ್ಟು ಸಲ ಆದರೂ ಅದೇ ಅಜ್ಜಿನಲ್ಲ ಅಂದೆ ನಾನು. ಆಯಿತು. ಹೊರಟ್ಟಿ ಸಾಹೇಬರು ಮೊನ್ನೆ ಒಂದು ಮಾತು ಹೇಳಿದರು. ಏನು ಹೇಳಿದರು ಅಂತಂದ್ರೆ, ಒಲಿ ಸರಿ ಇದ್ದರೆ ತಲೆ ಸರಿ ಇರ್ತದಂತ. ಒಲಿ ಸರಿ ಇದ್ದರೆ ತಲೆ ಸರಿ ಇರ್ತದೆ. ಆಗ ನಮ್ಮ ಒಲೆ ಭಾಳ ಸರಿ ಐತೆ. ಆ ಕಾರಣಕ್ಕಾಗಿ ನಾನು ಇಷ್ಟೆಲ್ಲ ಸಾಧನೆ ರಿಸರ್ಚ್ನಲ್ಲಿ ಬೆಳಗ್ಗೆ 7 ಗಂಟೆಯಿಂದ ರಾತ್ರಿ 9ರವರೆಗೆ ಕೂತ್ರೂ ನನಗೆ ಕೇಳ್ತಿದ್ದಿಲ್ಲ. ಒಂದು ಸಲ ಏನಾಯ್ತು, ರಾತ್ರಿ 9ಕ್ಕೆ ಮನೆಗೆ ಹೋಗ್ತಿದ್ದೆ ನಾನು. ಒಂದು ಸಲ ಏನೋ ಕೆಲಸ ಮಾಡ್ಕೋತ ಕೂತ ಡಿಪಾರ್ಟ್ಮೆಂಟ್ನಲ್ಲಿ 10 ಆಯಿತು. ಆವಾಗ ಫೋನು ಮಾಡಲಿಲ್ಲ ನಮ್ಮ ಮಿಸ್ಸಸ್ಸು. ಮನೆಗೆ ಹೋದೆ, ಮುಖ ಉಬ್ಬಿಸ್ಕೊಂಡು ಕೂತಿದ್ರು. ನಾಳೆ ಹೋದ ಕೂಡಲೇ ಒಂದು ಮಾತು ಹೇಳಿದರು, ನಾಳೆ ನಿಮ್ಮ ಖಾಜಾ ಪೀರ್ ವೈಸ್ ಚಾನ್ಸಲರ್ ಇದ್ರು ಅವಾಗ, ನಾಳೆ ನಿಮ್ಮ ವಿ ಸಿ ಕಡೆ ನಾನು ಕರ್ಕೊಂಡು ಹೋಗ್ರಿ. ಯಾಕಪ್ಪ, ಇವಕ್ಕೇನು ಕಂಪ್ಲೇಂಟ್ ಇಲ್ಲ, ಕಂಪ್ಲೇಂಟ್ ಮಾಡೋದೈತೆ ನನಗೆ. ಇಲ್ಲ, ಹೇಗೂ ನೀವು ಅಲ್ಲೇ ರಾತ್ರಿ ಇರ್ತೀರಿ, ಹಗಲೂ ಇರ್ತೀರಿ, ಆ ವಾಚ್ಮನ್ನ ಪಗಾರನೂ ಇವ್ರಿಗೆ ಕೊಟ್ಬಿಡು ಅಂತ ಹೇಳ್ತೀನಿ, ಅದಕ್ಕೆ ಕರ್ಕೊಂಡು ಹೋಗ್ರಿ. ಇಷ್ಟೊಂದು ನನಗೆ ಒಲಿ ಭಾಳ ಸರಿ ಅದ, ನನ್ನ ಕೆಲಸಕ್ಕೆ ಭಾಳ ಪ್ರೋತ್ಸಾಹ ಕೊಟ್ಟರು. ಅವರಿಗೆ ನಾನು ಈ ತುಂಬಿದ ಸಭೆಯಲ್ಲಿ ಕೃತಜ್ಞತೆ ಸಲ್ಲಿಸ್ತಾ ಇದ್ದೀನಿ. ಮತ್ತು ಇನ್ನೊಬ್ಬರಿಗೆ ಕೃತಜ್ಞತೆ ಸಲ್ಲಿಸಬೇಕಾದಂಥ ಕಾರಣ ಏನಂತಂದ್ರೆ, ನಾನು ರಿಟೈರ್ಡ್ ಆಗಿ 12 ವರ್ಷ ಆಯಿತು. 12 ವರ್ಷ ಆದ್ರೂ ನನ್ನ ಸ್ನೇಹಿತರು, ವಿಶ್ವವಿದ್ಯಾಲಯದ ಶಿಕ್ಷಕರು ಮತ್ತು ಸಂಶೋಧನಾ ವಿದ್ಯಾರ್ಥಿಗಳು ರಿಟೈರ್ಡ್ ಆಗಿನೂ 12 ವರ್ಷದ ನಂತರನೂ ಇಷ್ಟು ನೆನಪಿಟ್ಟುಕೊಂಡು ಇಂಥ ಅದ್ದೂರಿ ಕಾರ್ಯಕ್ರಮ ಮಾಡಿದ್ದಾರಲ್ಲ, ಅವರಿಗೆ ನನ್ನ ಶಿರಸಾಷ್ಟಾಂಗ ನಮಸ್ಕಾರ. ನನಗೆ ಗೊತ್ತಿರುತ್ತೆ. ಇಷ್ಟು ಹೇಳಿ ನನ್ನ ಮಾತುಗಳನ್ನು ಮುಗಿಸ್ತಾ ಇದ್ದೇನೆ.
Thank you, sir. Now I request Professor M.M. Shikare, sir, to address the gathering.
Respected Professor Walikar, Mrs. Walikar, Professor Nigalanj Gappa, Professor Shiral Shetty, Professor Vedamurthy, Professor Nagesh, Professor Ramani, Professor Sridevi, Professor Natikar, Professor Hampiali, other dignitaries on the dais, past faculty members, Professor Bujurge, Professor Basnarmat, Professor Basanagoda, the participants we have come for this conference. Good afternoon to everyone, and a warm welcome to this inaugural function of the two-day conference. As already pointed out by the anchor, so this conference is being organized, two-day conference, today and tomorrow, 10th April and 11th April, on mathematical sciences and their applications, in honor of Professor H.B. Walikar, on completion of his completing 75 years to his age. It was so, first of all, I wish on behalf of all the participants and all the dignitaries on dais, a very happy birthday, a very happy 75th year to Professor Walikar. May God bless him with a good health and happiness in his life, forever, forever. So, as has been mentioned here, that Professor Walikar is basically a professor of mathematics, teacher of mathematics, researcher of mathematics. And his contributions have been mentioned here, that. Some of the highlights that says that he's supposed to be ranked 6th in the work of domination theory in the world. So the work should be seem to be very significant. The ranking is not made by Professor Walikar, but the ranking is made by some agency, some people. So the work for us to evaluate his work, so the some of the highlights of his work, he's supposed to be one of the very good person in domination theory. Then the second thing, he guided 22 students for PhD degree and 5 students for MPhil degree. I think for the mathematics person, for mathematics professor, 22 is a very good number. We spent 40 years, 45 years, and our experience is that the average number of PhD students produced by a good professor is about 10 to 12, average number. In comparison to the 10 to 12, this 22 is supposed to be a very good number, a significant number. And moreover, this is not only the guiding the students, the quality of the research, the number of publications in national, international journal, that gives the recognition to the person, that gives the recognition to the department. How this department is recognized by the other people, other universities? That is on the basis of the programs given by the department. The teaching at the department, the research work and the publication, the project carried out the department. And I think this Harvard University Department of Mathematics have got a very good recognition outside because the people like Walikar and other faculty members have tried their best, have worked very hard for the department, carried out a very strong research. So we have come to recognize, to appreciate his work, to appreciate his contribution to mathematics. And then some of the things that he is an administrator also. Some of the points which have been mentioned, he created a lot of facilities for the students, library facility for the students, with the help of International Society for Sri Krishna Conscience ISKCON. He started some projects like providing the meal on a subsidized basis, meal for 5 rupees to the students. So these are, I think, he knew the problems exactly. As Steve Jobs has said, if you can define the problems, you can identify the problems, probably there is a solution. In mathematics also, we can say that if your problem is clear, there is likely to get the solution. I think this attitude might have helped to improve the functioning of the university, that he could have identified where are the problems, where are the difficulties, what are the exact difficulties, what are the exact problems. Perhaps he could have tried that way, tried that approach, and that's why he was successful to raise the administrative capabilities of the university. So I know there are people who are academicians but may not be good administrators. There are people who are good administrators but need not be academician. Here it is a combination. A person is academician, sound academician, and able administrator. Right. And as he mentioned, that he is a good writer in Kannada language. He wrote several languages. How can he do it? One of the book is Sense in Nonsense. Wrote a book. It was one of the bestseller book. As a mathematician, sense in nonsense. I asked what is the converse of that? Because as a mathematical statement, nonsense in sense. Perhaps he can think of nonsense in sense, and it is true up to some level. So very good writer, a academician, administrator, good writer in Kannada, and it is not a casual writer, but it is a book which are bestseller in Kannada. And more than that, he is supposed to be involved in some societies. Like I read, that supporting Devdasi Children's School, very unusual. then running some programs for the high school teachers, for students. Apart from the high level mathematics, going to the society, understanding the problem, getting involved, I think it matters satisfaction. Person, he doesn't think of what he is, where he is, but he think of what he needs to do, where are the problems. No matter whether we teach at the PG level or we teach at the high school level, the question is improving the quality. So it's going to the society and doing a lot of things. So combination of academician, administrator, writer, and social activity, a very unique combination, very unique combination. And for me, why his contributions are more important, more significant. I knew that he has come from a very small town, Eragal, Bijapur district, a family which do not have educational background, a parent who do not know education, a village that may not have good facilities of school. Starting his journey from Eragal and developing himself as such a teacher, efficient teacher, setting an example, this is something new. This is very unbelievable, incredible journey for Professor Walikar. But remind me, God has some wonders. God has some wonders. God converts sand into pearls. God converts mine, that coal mines. Diamonds are found in coal mines. And moreover, you know that is why Walikar has so large section of the society. He may have faced several problems, may have seen very large cross section of the society. Good experience, bad experience. And as an academician, he was fortunate. He could do that kind of academic work because he could come in contact with the people like E. Sampath Kumar he mentioned. Professor B.D. Acharya. Professor B.D. Acharya, we studied, he was our friend, he was our guide. Any person who was staying with Professor B.D. Acharya used to talk all the time only mathematics. Such a wonderful person. He stayed with Hedit Nimi. He stayed with Renu Laskar. And then Peter Slatters. He has some contributions with Ivan Gutman. Ivan Gutman, we also have the people. But a person who has published about 1,600 papers, Ivan Gutman have published 1,600 papers in a highly, he's supposed to be father of the spectral graph theory. And Professor Walikar has some paper with Ivan Gutman. So if you have some such type of paper, that gives you more energy, that gives you more enthusiasm. Person, because I think staying in a company of good people is like walking through the perfume shop. When you visit perfume shop, the shopkeeper to taste, they rub some perfume on your hand. You may buy perfume, you may not buy perfume, but you are bound to carry the fragrance with you. Like that, when one stays in company of good people, you get the environment, you see what kind of things, how they work, how they guide, how they carry out the research, and I think that makes the impact on your work, research work you are teaching. Professor Walikar is fortunate in that sense. He could get the company of so many people, and that's why he could do things, because if somebody does good kind of work, there is some reason. And I think one of the factors that is true, that he could get the company, that is also a wonderful thing, that. Somebody has said life is gift. Life is gift to us, God's gift. One should realize it. Professor Walikar realized it, life is a gift, and tried to make best out of it. So he did it. He tried to make a best of things, tried to make very good research, tried to help the students. Ultimately, satisfaction. What is the success of the life? Success of the life, more than success, I think it is satisfaction is a more important factor. And I think he tried whole life in helping to the other people. When you do something for others, something good happens for you. You have planted the seed so many years back, and the fruits have come. The return is coming in this way. People are expressing gratitude to you, feliciting at the age of 75 years, expressing their gratitude, their love, their affection, and wishing you good luck for your future. And I would say, finally, that organizing this conference serves several purposes. Expressing gratitude is one thing. Recognizing his achievement is its part. But as you notice, this conference gave the opportunity to come to several people at one place. That's why some past faculty members, some students of some, Walikar sir students have come, their students have come. So, grand students of Walikar students sir have also come here, that. So many people, I'm just watching, that many students of this department, they express, they meet Bushnurmat sir, Baswan Gowda, Madam, Buzurke, and they have that some satisfaction, some love of gratitude. So the organization of the conference also serve this purpose, is give opportunity to people to come together. And we hope we will get the opportunity to celebrate 100th birthday of Walikar. Because now it is possible. Why it is possible? With the help of AI, artificial intelligence, that people are trying to raise their age, that. And that's why they predict that it is possible to live for 100 years, 120 years, 140 years. So maybe Walikar sir will certainly like to go through some hits from the AI and would like to see how to keep the health in good situation. So we hope we will get the opportunity to celebrate 100th year of Professor Walikar. So once again, I express my gratitude to him. I wish him a good luck, and may God bless him a good health and happiness in his life. Thank you very much for the organizers. Thanks to very much for the organizers giving me the honor as a chief guest for this function. Of course, I have come from a small village. I have seen some broad cross-section of the society, but I never stop, never leave it, that. That is my principle, do or die. That was the principle I adopted in my life. General Secretary of the Indian Mathematical Society is not a small thing. It is a coveted post. The society which was founded about 120 years ago, and we have, whose office bearers were top mathematicians in India, a person from non-educated family who has come from a family with no educational background, he becomes the General Secretary of the Indian Mathematical Society. I think this is miracle. Even I don't believe how it happens. But if you try systematically, believe yourself, respect the older people, and then it is possible. Then it is possible. And that happened with me. So thank you very much for inviting me and for honoring. It was a wonderful felicitation. It was a first kind in my life that kind of felicitation we did it. So thank you once again. Thank you very much. With this, I end up my. Have a nice time. Okay, thank you.
ಥ್ಯಾಂಕ್ ಯು ಸರ್. ವಿಜಯಪುರದ ಜ್ಞಾನ ಯೋಗಾಶ್ರಮದ ಶ್ರೀ ಸಿದ್ದೇಶ್ವರ ಸ್ವಾಮಿಗಳು, ಧಾರವಾಡ ಶ್ರೀ ಕುಮಾರಸ್ವಾಮಿಗಳ ತಪೋವನದ ದಿವ್ಯ ದೇವಾಲಯದಲ್ಲಿ ನಡೆದ ರಾಷ್ಟ್ರ ಮತ್ತು ಅಂತಾರಾಷ್ಟ್ರೀಯ ಶಿಕ್ಷಣ ಚಿಂತನೆಯಲ್ಲಿ ಪ್ರೊಫೆಸರ್ H.B. ವಾಲಿಕರ್ ಸರ್ ಅವರ ಪಾಲ್ಗೊಂಡಿದ್ದರು. ಸೊ ಅದರ ಪ್ರಯುಕ್ತವಾಗಿ ಸವಿ ನೆನಪಿನ ಕಾಣಿಕೆ ಪ್ರಕಾಶ್ ಮರಿಗೌಡ ಸರ್ ಇವರಿಂದ ಕಟ್ಟಡ ವಿಭಾಗ. Thank you, sir. Leadership is not about a position. It's about a action, vision, and impact. Today, we have honor of being in the presence of such a remarkable leader, Professor Nijlingappa Y. Mattihal, sir, whose dedication, integrity, and wisdom continue to inspire and influence the countless lives. With a great honor, I request Professor Nijlingappa Y. Mattihal, sir, for the presidential remark.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರಗಳು. ಕರ್ನಾಟಕ ವಿಶ್ವವಿದ್ಯಾಲಯದ ಗಣಿತ ವಿಜ್ಞಾನ ವಿಭಾಗವು ಡಾಕ್ಟರ್ H.B. ವಾಲಿಕರ್ ಅವರ ಅಮೃತ ಮಹೋತ್ಸವದ ಸಂದರ್ಭದಲ್ಲಿ ಹಮ್ಮಿಕೊಂಡಿರುವ ಗಣಿತ ವಿಜ್ಞಾನ ಮತ್ತು ಅದರ ಉಪಯೋಗಗಳು ಎಂಬ ವಿಷಯದ ಮೇಲೆ ಒಂದು ದಿನದ ರಾಷ್ಟ್ರೀಯ ವಿಚಾರ ಸಂಕಿರಣ ಮತ್ತು ನಾಳೆ ಅಮೃತ ಮಹೋತ್ಸವದ ಸಮಾರಂಭದ ಕಾರ್ಯಕ್ರಮವನ್ನು ಇವತ್ತು ಉದ್ಘಾಟನೆಯನ್ನು ಮಾಡಿ ಹಲವು ಮಹನೀಯರು ಪ್ರೊಫೆಸರ್ ವಾಲಿಕಾರ್ ಸರ್ ಅವ್ರ ಬಗ್ಗೆ ಒಳ್ಳೆಯ ಮಾತುಗಳನ್ನಾಡಿದ್ದಾರೆ. ಈ ಸಮಾರಂಭದ ಕೇಂದ್ರ ಬಿಂದುಗಳು ಈ ವಿಶ್ವವಿದ್ಯಾಲಯದ ವಿದ್ಯಾರ್ಥಿಯಾಗಿ ರೂಪುಗೊಂಡು ಕರ್ನಾಟಕ ವಿಶ್ವವಿದ್ಯಾಲಯಕ್ಕೆ ಹೊಸ ರೂಪವನ್ನು ಕೊಟ್ಟಂಥ, ಹಾಗೆ ಈ ವಿಶ್ವವಿದ್ಯಾಲಯಕ್ಕೆ ವಿದ್ಯಾರ್ಥಿಯಾಗಿ ಓದಲು ಬಂದ ಮೊದಲು ಮೆಟ್ಟಿಲ ಮೇಲೆ ನಿಂತ ಒಬ್ಬ ಹುಡುಗ ಈ ವಿಶ್ವವಿದ್ಯಾಲಯದ ಆಡಳಿತ ಶಿಖರವನ್ನು ತಲುಪಿ ನಿಂತ ವ್ಯಕ್ತಿತ್ವವನ್ನು ಕುರಿತು 2 ದಿನಗಳ ಕಾಲ ಈ ವೇದಿಕೆ ಮೇಲೆ ಚರ್ಚೆಯಾಗ್ತಾ ಇರುವುದು ನಿಜಕ್ಕೂ ನಮಗೆಲ್ಲ ಸಂತೋಷದ ಸಂಗತಿ. ಈ ಸಮಾರಂಭದ ಕೇಂದ್ರ ಬಿಂದುಗಳು ನನ್ನ ಮತ್ತು ನನ್ನಂಥ ಅನೇಕ ಜನರಿಗೆ ಬದುಕನ್ನು ಕೊಟ್ಟಂಥ ಪ್ರೊಫೆಸರ್ H.B. ವಾಲಿಕಾರ್ ಸರ್ ಅವರೇ, ಮಾತೃ ಸ್ವರೂಪರಾದಂಥ ಶ್ರೀಮತಿ ಅನ್ಸೂಯ ತಾಯಿಯವರೇ, ಹಾಗೆ ಪ್ರೊಫೆಸರ್ M.M. ಸಿಕಾರಿ ಅವರೇ, ಪ್ರೊಫೆಸರ್ ವೇದಮೂರ್ತಿಯವರೇ, ಪ್ರೊಫೆಸರ್ ಹಂಪಿಹೊಳಿಯವರೇ, ಪ್ರೊಫೆಸರ್ ರಮಣೆ ಅವರೇ, ಪ್ರೊಫೆಸರ್ ಸುಭಾಷ್ ಚಂದ್ರ ನಾಟಿಕಾರ್ ಅವರೇ, ಪ್ರೊಫೆಸರ್ ಸಿರಾಳ್ ಶೆಟ್ಟಿ ಅವರೇ, ಪ್ರೊಫೆಸರ್ ಶ್ರೀದೇವಿ ಅವರೇ, ಪ್ರೊಫೆಸರ್ ನಾಗೇಶ್ ಅವರೇ, ವೇದಿಕೆ ಮೇಲಿರ್ತಕ್ಕಂಥ ಉಳಿದ ಗಣ್ಯರೇ, ವೇದಿಕೆ ಮುಂಭಾಗದಲ್ಲಿ ನಿಜವಾಗಲೂ ಸಾಹಿತ್ಯ, ಶಿಕ್ಷಣ ಮತ್ತು ಸಾಂಸ್ಕೃತಿಕ ರಾಯಭಾರಿಯಾಗಿ ಕೆಲಸ ಮಾಡಿದಂಥ ಪ್ರೊಫೆಸರ್ ಸನದಿ ಅವರು ಹೇಳಿದರು, ಒಂದು ಹದ ನೋಡಿ ಒಂದು ಉತ್ತಮವಾದಂಥ ಬೀಜವನ್ನು ಬಿತ್ತಿದರೆ ಆ ಎಂಥ ಫಲ ಕೊಡ್ತೈತೆ ಅನ್ನೋದಕ್ಕೆ ವಾಲಿಕಾರ್ ಅಂತ ಪ್ರತಿಭೆ ಈ ನೆಲದಲ್ಲಿ ಅರಳಲಿಕ್ಕೆ ಅವರು PhDಗೆ ಸೀಟು ಕೊಡಿಸಿ ಅವರ ಬೆಳಿಲಿಕ್ಕೆ ಕಾರಣರಾದಂಥ ಸನದಿ ಸಾಹೇಬರಿದ್ದಾರೆ. ಮತ್ತು ವಿಶ್ವವಿದ್ಯಾಲಯದ ಗಣಿತ ವಿಭಾಗದಲ್ಲಿ ಕೆಲಸ ಮಾಡಿದಂಥ ಎಲ್ಲ ಪ್ರಾಧ್ಯಾಪಕರೇ, ಗಣಿತ ವಿಭಾಗದ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿಗಳೇ, ವಿಶ್ವವಿದ್ಯಾಲಯದ ಎಲ್ಲ ವಿಭಾಗಗಳ ಪ್ರಾಧ್ಯಾಪಕರೇ, ಹಿರಿಯರೇ, ವಾಲಿಕರ್ ಅವರ ಅಭಿಮಾನಿಗಳೇ, ಈ ತುಂಬಿದ ಸಭೆಯಲ್ಲಿ ಕೂಡಿದ ತಮ್ಮೆಲ್ಲರಿಗೂ ನಾನು ಎದೆಯಲುವೆನಿಂದ ಶಿರಬಾಗಿ ನಮಸ್ಕಾರಗಳನ್ನು ಮಾಡ್ತಾ ಇದ್ದೇನೆ. ಒಂದೊಂದು ಸಂದರ್ಭದಲ್ಲಿ ಅವಕಾಶಗಳು ಹೇಗೆ ಸಿಗ್ತಾವೆ ಅಂತ ಹೇಳಿದರೆ, ವಾಲಿಕರ್ ಸರ್ ಅಂತ ಶ್ರೇಷ್ಠ ವ್ಯಕ್ತಿಗಳ ಈ ಸಮಾರಂಭದಲ್ಲಿ ನನ್ನಂಥ ಹುಡುಗನಿಗೆ ಅಧ್ಯಕ್ಷತೆ ವಹಿಸಿಕೊಳ್ಳುವಂಥ ಅವಕಾಶ ಸಿಕ್ಕಿದ್ದು ನಿಜಕ್ಕೂ ನನ್ನ ಜೀವನದಲ್ಲಿ ಸಿಕ್ಕಂಥ ಬಹಳ ದೊಡ್ಡ ಭಾಗ್ಯ ಅಂತ ಭಾವಿಸ್ಕೊಂಡಿದ್ದೇನೆ. ಸಂಘಟಕರಿಗೆ ಆರಂಭದಲ್ಲಿಯೇ ನಾನು ಕೃತಜ್ಞತೆಗಳನ್ನು ಹೇಳಲಿಕ್ಕೆ ಬಯಸ್ತೇನೆ. ಪ್ರೀತಿ ತೋರುವವರ ಔದಾರ್ಯವೇ ಹೊರತು ಪಡೆಯೋನ ಯೋಗ್ಯತೆ ಅಲ್ಲ ಅನ್ನುವಂಥ ಮಾತು ನನಗೆ ಈಗ ನೆನಪಿಗೆ ಬರ್ತಾ ಇದೆ. ಈ ಪ್ರೀತಿ ನಿಮ್ಮ ಔದಾರ್ಯವೇ ಹೊರತು ನನ್ನ ಯೋಗ್ಯತೆ ಅಲ್ಲ ಅನ್ನುವಂಥದ್ದನ್ನು ಕೂಡ ನೆನಪಿಸಿಕೊಂಡು ನನ್ನ ಮಾತುಗಳನ್ನು ಆರಂಭಿಸುತ್ತೇನೆ. ಶತಾಯುಷಿಗಳಾಗಿ ಬಾಳಲಿ ಎಂಬ ಹಾರೈಕೆ ಅತ್ಯಂತ ಹಿರಿದಾದ ಹಾರೈಕೆ ಎನಿಸಿರುವ ನಮ್ಮ ಪರಂಪರೆಯಲ್ಲಿ ಡಾಕ್ಟರ್ HP ವಾಲಿಕಾರ್ ಸರ್ ಒಂದು ಅಪ್ಪಟ ದೇಶಿ ಪ್ರತಿಭೆಯ ಚೇತನಕ್ಕೆ ಈಗ ಅಮೃತ ಮಹೋತ್ಸವದ ಸಂದರ್ಭ. ಅನೇಕ ಹೋರಾಟಗಳ ಮಧ್ಯೆ ಪ್ರೊಫೆಸರ್ ವಾಲಿಕಾರ್ ಸರ್ ಅವರು 75 ವರ್ಷಗಳ ಸಂಘರ್ಷದ ತ್ಯಾಗ ಜೀವನವನ್ನು ಪೂರ್ಣಗೊಳಿಸಿದ ಸಂದರ್ಭ ಕೂಡ ಇದಾಗಿದೆ. ಈ ಅವಧಿಯಲ್ಲಿ ಪ್ರೊಫೆಸರ್ ವಾಲಿಕಾರ್ ಸರ್ ಅವರ ಸಂಪರ್ಕಕ್ಕೆ ಬಂದು ಅವರ ಬೋಧನೆ, ಅವರ ಮಾರ್ಗದರ್ಶನ, ಅವರ ಸಹಾಯ ಸಹಕಾರ, ಆಶೀರ್ವಾದದಿಂದ ತಮ್ಮ ಜೀವನವನ್ನು ಪಾವನಗೊಳಿಸಿಕೊಂಡು ಬಾಳನ್ನು ಸಮೃದ್ಧಗೊಳಿಸಿಕೊಂಡ ನಮ್ಮಂಥವರ ಪಾಲಿಗೆ ಇದು ಒಂದು ವಿಶೇಷ ಹಬ್ಬದಾಚರಣೆಯ ಸಂದರ್ಭವೂ ಹೌದು. ಈ ಸಂದರ್ಭ ವಾಲಿಕಾರ್ ಸರ್ ಕ್ಷೇತ್ರದ ಗಣಿತಶಾಸ್ತ್ರದ ಮೇಲೆ ರಾಷ್ಟ್ರೀಯ ವಿಚಾರ ಸಂಕಿರಣ ನಡೆಸುತ್ತಿರುವುದು ಒಂದು ಅಮೃತ ಗಳಿಗೆ ಅಂತ ನಾನು ಭಾವಿಸಿಕೊಂಡಿದ್ದೇನೆ. ಡಾಕ್ಟರ್ HP ವಾಲಿಕಾರ್ ಸರ್ ಅವರಿಗೆ ಈಗ 70 ವಸಂತಗಳನ್ನು ಪೂರ್ಣಗೊಳಿಸಿದ್ದಾರೆ. ಈ 75 ವರ್ಷಗಳಲ್ಲಿ ಅವರು 75 ವರ್ಷಗಳ ಕಾಲ ಸೂರ್ಯ ಚಂದ್ರರನ್ನು ಕಂಡವರು. ಈ 75 ವರ್ಷಗಳ ಕಾಲ ಬಿಸಿಲು ಬೆಳದಿಂಗಳಕ್ಕೆ ತಮ್ಮ ಮೈ ಮನಗಳನ್ನು ಒಡ್ಡಿದವರು. ಈ 75 ವರ್ಷಗಳ ಕಾಲ ಹಗಲು ರಾತ್ರಿಗಳನ್ನು ಕಂಡವರು. 75 ವರ್ಷಗಳ ಕಾಲ ಕತ್ತಲೆ ಬೆಳಕಿನಲ್ಲಿ ಬದುಕಿದವರು. ಈ ಸುದೀರ್ಘ ಅವಧಿಯಲ್ಲಿ ಸಮಾಜದ ಮಧ್ಯದಲ್ಲಿದ್ದುಕೊಂಡು ತಮ್ಮ ಪ್ರೀತಿ ಮತ್ತು ಅಂತಃಕರಣೆಯ ಎದೆವರತೆಯನ್ನು ನಿರಂತರವಾಗಿ ಹರಿಸಿದವರು ಪ್ರೊಫೆಸರ್ HP ವಾಲಿಕಾರ್ ಸರ್ ಅವರು. ಹಾಗೆ ಸಮಕಾಲೀನ ಸಮಾಜವು ಅವರಿಗೆ ಅರ್ಪಿಸಿದ ಬೇವು ಬೆಲ್ಲದ ಎಡೆಯನ್ನು ಅಷ್ಟೇ ಸಮಾಧಾನದಿಂದ ಸ್ವೀಕರಿಸಿದವರು. ಒಂದು ಮಾತು ನೆನಪಿಗೆ ಬರ್ತದೆ, ಈ ದೇಶದಲ್ಲಿ, ಈ ಪ್ರಪಂಚದಲ್ಲಿ ಸತ್ಯವಂತರಿಗೆ ಅನೇಕ ತೊಂದರೆಗಳಾಗಿವೆ. ಸತ್ಯವಂತರಿಗೆ ಅನೇಕ ತೊಂದರೆಗಳನ್ನು ಎದುರಿಸುವಂಥ ಸಂದರ್ಭ ಬಂದಿದೆ. ವಾಲಿಕಾರ್ ಅವರು ಸತ್ಯಕ್ಕಾಗಿ ಹೋರಾಟ ಮಾಡಿದ್ದಕ್ಕಾಗಿ ಅನೇಕ ಸಮಸ್ಯೆಗಳನ್ನು ಎದುರಿಸುವಂಥ ಸಂದರ್ಭ ಈ ನೆಲದಲ್ಲಿ ಆಗಿದೆ. ಸತ್ಯ ಗೊತ್ತಾದಾಗ ಮತ್ತೆ ಅಂಥ ವ್ಯಕ್ತಿಗಳು ಸನ್ಮಾನಕ್ಕೆ ಒಳಗಾದಂಥ ಸಂದರ್ಭಗಳು ಸಾಕಷ್ಟಿವೆ. ಸಹನೆ ಅಸಹನೆ ಮಧ್ಯೆ ನಡೆದಂಥ ಸಂಘರ್ಷ, ಸತ್ಯ ಅಸತ್ಯದ ಮಧ್ಯದಲ್ಲಿ ನಡೆದಂಥ ಸಂಘರ್ಷ, ನ್ಯಾಯ ಅನ್ಯಾಯಗಳ ಮಧ್ಯೆ ನಡೆದಂಥ ಸಂಘರ್ಷದಲ್ಲಿ ಅನೇಕ ಸತ್ಯವಂತರು ಕಹಿಯನ್ನು ಉಂಡಾರೆ, ಬೇವು ಬೆಲ್ಲದ ಎಡಿಯನ್ನು ಊಟ ಮಾಡಿದ್ದಾರೆ. ವಾಲಿಕಾರ್ ಅವರು ಸಮಾನತೆಗಾಗಿ, ಸಮಾಜವನ್ನು ಕಟ್ಟಬೇಕನ್ನೋ ಉದ್ದೇಶಕ್ಕಾಗಿ ಮಾಡಿದಂಥ ಕೆಲಸ ಅವರ ನಿವೃತ್ತಿಯ ದಿವಸ ಇಂಥ ಒಂದು ಸಂದರ್ಭವನ್ನು ಅನುಭವಿಸಿ ಮನೆಗೆ ಹೋಗಬೇಕಾಗಿತ್ತು, ಹೋಗಲಿಕ್ಕೆ ಆಗಲಿಲ್ಲ. ಸಹನೆ ಮತ್ತು ಅಸಹನೆಯ ಮಧ್ಯೆ, ಸತ್ಯ ಮತ್ತು ಅಸತ್ಯದ ಮಧ್ಯೆ ನಡೆದ ಸಂಘರ್ಷಕ್ಕಾಗಿ ವಾಲಿಕಾರ್ ಅವರಿಗೆ ಆ ದಿನ ಸಿಗದ ಗೌರವ, ಸತ್ಯ ಏನು ಅಂತೇಳಿ ಸಮಾಜಕ್ಕೆ ಗೊತ್ತಾದ ಮೇಲೆ ಅಂತ ಅಮೃತ ಗಳಿಗೆ ಇವತ್ತು ಕೂಡಿ ಬಂದಿದೆ. ನಿಮಗೆಲ್ಲ ಗೊತ್ತು, ಸಾಕ್ರಟಿಸ್ ಗೊತ್ತು, ಬಸವಣ್ಣ ಗೊತ್ತು, ಜೀಸಸ್ ಕ್ರಿಸ್ತನ ಬಗ್ಗೆ ನಮಗೆ ಗೊತ್ತು, ಗಾಂಧಿ, ಹರಿಶ್ಚಂದ್ರ, ಇವರೆಲ್ಲರಿಗೆ ಈ ದೇಶ, ಪ್ರಪಂಚ ಕೊಟ್ಟಂತ ಕೊಡುಗೆ ಏನು ಅಂತೇಳಿ ಪ್ರಶ್ನೆ ಮಾಡಿಕೊಂಡ್ರೆ ವಾಲಿಕರ್ ಅವ್ರಿಗೆ ಕೊಟ್ಟ ತೊಂದರೆ ಏನು ನಮಗೆ ಹೊಸದು ಅನಿಸುವುದಿಲ್ಲ. ಧಾರ್ಮಿಕ ವ್ಯವಸ್ಥೆಯ ಸುಳ್ಳುಗಳನ್ನು ಪ್ರಶ್ನಿಸಿದ ಸಾಕ್ರಟಿಸನಿಗೆ ನಾವೆಲ್ಲ ವಿಷ ಕುಡಿಸಿದ್ದೇವೆ. ಯಾವ ಕಾರಣಕ್ಕಾಗಿ? ಧಾರ್ಮಿಕ ವ್ಯವಸ್ಥೆಯನ್ನ ಪ್ರಶ್ನಿಸಿ, ವ್ಯವಸ್ಥೆಯನ್ನ ಪ್ರಶ್ನಿಸುವುದನ್ನ ಯುವಕರಲ್ಲಿ ತುಂಬಿದ ಕಾರಣಕ್ಕಾಗಿ ಸಾಕ್ರಟಿಸನಿಗೆ ವಿಷ ಕುಡಿಸಿದ್ದೇವೆ. ಜಾತಿ ವ್ಯವಸ್ಥೆಯ ಮೇಲು ಕೀಳುಗಳನ್ನು ನಿವಾರಿಸಿ ಸಮಾಜದ ನಿರ್ಮಾಣಕ್ಕೆ ಯತ್ನಿಸಿದಂತ ಬಸವಣ್ಣನನ್ನ ದುರಂತಕ್ಕೆ ತಳ್ಳಿದ್ದೇವೆ. ಹಾಗೆ ಧಾರ್ಮಿಕ ವ್ಯವಸ್ಥೆಯ ಕುತಂತ್ರಗಳನ್ನು ಸರಿಪಡಿಸಲು ಯತ್ನಿಸಿದಂತ ಜೀಸಸ್ ಕ್ರಿಸ್ತನಿಗೆ ಶಿಲುಬೆಗೇರಿಸಿದ್ದೇವೆ. ಧಾರ್ಮಿಕ ಹಿಂಸಾಚಾರಗಳನ್ನು ತಡೆಗಟ್ಟಲು ಯತ್ನಿಸಿದಂತ ಗಾಂಧಿಗೆ ಮೂಲಭೂತವಾದಿಗಳು ಬೀದಿಯಲ್ಲಿ ಎದೆಗೆ ಗುಂಡಿಟ್ಟು ಕೊಂದದ್ದು ನಮಗೆ ಗೊತ್ತು. ಸತ್ಯ ಹೇಳಿದ್ದಕ್ಕಾಗಿ ಹರಿಶ್ಚಂದ್ರ ಸುಡುಗಾಡ ಕಾಯುವಂತ ಸಂದರ್ಭ ಬಂದದ್ದು ನಮಗೆಲ್ಲ ಗೊತ್ತಿರುವಂಥದ್ದು. ಈ ಲೋಕದಲ್ಲಿ ಇಂಥ ಸಂಘರ್ಷಗಳು, ಸತ್ಯವಂತರಿಗೆ ಹಿಂಸೆಗಳು ನಿರಂತರವಾಗಿ ನಡೆಯುತ್ತಲೇ ಬಂದಿವೆ. ವಾಲಿಕಾರ್ ಅವರು ಈ ನೆಲದಲ್ಲಿ ಸಮಾನತೆಯನ್ನು ತರಬೇಕು ಎನ್ನುವ ಕಾರಣಕ್ಕಾಗಿ ನಾವು ಈ ವಿಶ್ವವಿದ್ಯಾಲಯದಲ್ಲಿ ನೆನಪಿಸಿಕೊಂಡಾಗ ಪಾವಟೆ ಅವರನ್ನು ನೆನಪಿಸಿಕೊಳ್ತೀವಿ. ಪಾವಟೆ ಅವರಿಗಿಂತ ಕಡಿಮೆಯಲ್ಲದ ಕೆಲಸವನ್ನ ವಾಲಿಕಾರ್ ಅವರು ಏನು ಮಾಡಲಿಲ್ಲ. ಪಾವಟೆ ಅವರ ಸಮಸಮನಾದಂಥ ಕೆಲಸವನ್ನು ಮಾಡಿದರು. ಆದರೆ ಪಾವಟೆಯವರ ಕಾಲದಲ್ಲಿ ಹಾಗಿರಲಿಲ್ಲ. ಪಾವಟೆಯವರು ಮಾಡಿದ್ದು ಒಂದೇ ಸಮುದಾಯದ ಜನಗಳಿಗೆ ಸಹಾಯ ಮಾಡಿದರು. ಸತ್ಯವನ್ನ, ನನ್ನ ಮಾತುಗಳು ಕೆಲವರಿಗೆ ವಿಷ ಅನಿಸ್ಬೋದು, ನೋವು ಅನಿಸ್ಬೋದು, ಚುಚ್ಚಬಹುದು, ಆದರೆ ಸತ್ಯವನ್ನ ಹೇಳಲೇಬೇಕು. ಪಾವಟೆಯವರ ಕಾಲಕ್ಕೆ ಬೇರೆಯವರಿಗೆ ಮಾಡಬೇಕಂದ್ರೆ ಬೇರೆ ವರ್ಗದ ಜನಗಳು ಓದಿರ್ಲಿಲ್ಲ. ಅದೊಂದು ಮೋಕ ಅವರಿಗೆ. ಒಂದೇ ವರ್ಗದ ಸಮುದಾಯದ ಜನಗಳಿಗೆ ಸಹಾಯ ಮಾಡುವಂತ ಕಾಲಿತ್ತು, ಮಾಡಿದ್ರು. ಹಾಗೆ ಮಾಡಿದ್ದಕ್ಕಾಗಿ ಪಾವಟೆ ಅವರು ಈ ನೆಲದಲ್ಲಿ ಪ್ರತಿಷ್ಠಾಪನೆ ಆದರೂ ಪೂಜೆಗೊಳ್ತಾ ಇದ್ದಾರೆ. ವಾಲಿಕಾರ್ ಅವರು ಈ ನೆಲದಲ್ಲಿ ಎಲ್ಲ ಸಮುದಾಯದ ಜನಗಳನ್ನು ತರಬೇಕು. ಪಾವಟೆ ಅವರ ಕಾಲದಲ್ಲಿ ನೋಡಿ ಯಾರೂ ಇಲ್ಲ, ಅಲ್ಲಿ ಮಹಿಳೆಯರಿಲ್ಲ, ಮೈನಾರಿಟಿ ಇಲ್ಲ, ದಲಿತರಿಲ್ಲ, ದೀನದಲಿತರಿಲ್ಲ, ಬಡವರಿಲ್ಲ, ಹಿಂದುಳಿದವರಿಲ್ಲ, ಯಾರು ಇರಲಿಲ್ಲ, ಓದಿರ್ಲಿಲ್ಲರಿ. ಅವಾಗ ಒಂದು ಅವಕಾಶ ಇತ್ತು. ಹಾಗಂತೇಳಿ ಪಾವಟೆ ಅವರು ಮಾಡಿದ್ದು ತಪ್ಪಂತ ನಾನು ಹೇಳುವುದಿಲ್ಲ. ಆದರೆ ವಾಲಿಕಾರ್ ಅವರು ಕೂಲಿ ಕಾರ್ಮಿಕರ ಮಕ್ಕಳನ್ನ, ದಲಿತರ ಮಕ್ಕಳ, ದೀನದಲಿತರ ಮಕ್ಕಳನ್ನ, ಎಲ್ಲರನ್ನು ಸಾಮಾಜಿಕ ನ್ಯಾಯವನ್ನ ಕೊಡಬೇಕನ್ನುವಂತ ಉದ್ದೇಶಕ್ಕಾಗಿ ಮಾಡಿದಂಥ ಕೊಡುಗೆ ಏನಿದೆ ನೋಡಿ, ಈ ವಿಶ್ವವಿದ್ಯಾಲಯದ ಇತಿಹಾಸದಲ್ಲಿ ಸುವರ್ಣಾಕ್ಷರಗಳಿಂದ ಬರೆದಿಡುವಂಥ ಕೆಲಸ ಅದು. ಈ ವಿಶ್ವವಿದ್ಯಾಲಯದ ಅನೇಕ ವಿಭಾಗಗಳಲ್ಲಿ ದಲಿತ ವರ್ಗದಿಂದ ಬಂದವರು ಮುಖ್ಯಸ್ಥರಾದರು, ಡೀನರಾದರು, ಸಿಂಡಿಕೇಟ್ ಮೆಂಬರ್ ಆದರು, ಅಧಿಕಾರಿಗಳಾದರು, ಎಲ್ಲ ಆದರು. ಯಾಕೆ ಆದರು ಅಂತ ಹೇಳಿದ್ರೆ ವಾಲಿಕಾರ್ ಅವರ ದೂರದರ್ಶತ್ವಕ್ಕೆ, ದೂರದೃಷ್ಟಿಗೆ ಸಾಕ್ಷಿಯಾಗಿ ಅವರೆಲ್ಲ ಅಂತ ಒಂದು ಅವಕಾಶ ಪಡಲಿಕ್ಕೆ. ನನ್ನಂಥವನು ಪ್ರಪಾತದಲ್ಲಿ ಬಿದ್ದವರನ್ನ ಮೇಲೆತ್ತುವ ಕೆಲಸವನ್ನು ಮಾಡಿದರು ವಾಲಿಕಾರ್ ಅವರು. ಅಂಧಕಾರದಲ್ಲಿ ಮುಳುಗಿದ ಪ್ರಪಾತದಲ್ಲಿ ಬಿದ್ದಂಥವರಿಗೆ ಕೈ ಕೊಟ್ಟು ಮೇಲೆತ್ತುವಂತ ಕೆಲಸ ಮಾಡಿದ್ರು. ಉದಾಹರಣೆಗೆ, ನಾನು ಅಸಿಸ್ಟೆಂಟ್ ಪ್ರೊಫೆಸರ್ ಇದ್ನಿ, ನನ್ನ ಪ್ರೊಫೆಸರ್ ಮಾಡಿದ್ರು. ಅಸಿಸ್ಟೆಂಟ್ ಪ್ರೊಫೆಸರ್ ಅನ್ನೋದು ಈ ವ್ಯವಸ್ಥೆಯಲ್ಲಿ ಅತ್ಯಂತ ಕೆಳಗಿರುವಂತ ಸ್ಥಾನ. ಅಸಿಸ್ಟೆಂಟ್ ಪ್ರೊಫೆಸರ್ಗಳಿದ್ದವರನ್ನ ಪ್ರೊಫೆಸರ್ಗಳು ಮಾಡಿದ್ರು. ಎಲ್ಲೂ ಪರ್ಮನೆಂಟ್ ಕೆಲಸ ಮಾಡಲಾರ್ದವ್ರನ್ನ ಅವ್ರ ಅನುಭವ ಇದೆಯಲ್ಲ, ನಮ್ಮ ರೂಲ್ ಹೇಳ್ತದೆ ವಿಶ್ವವಿದ್ಯಾಲಯ ಹೀಗಿರ್ಬೇಕು, ಹೌದು ಇರ್ಬೇಕ್ರಿ. ಇಲ್ಲದ ಪ್ರತಿಭಾವಂತರದಾರಲ್ಲ ಅವ್ರಿಗೇನು ಮಾಡಬೇಕು? ವಾಲಿಕರ್ ಅವ್ರ ಪ್ರಶ್ನೆ. ಅವನಿಗೆ ಪರ್ಮನೆಂಟ್ ಇರ್ಲಿಕ್ಕಿಲ್ಲ, ಸಂಬಳ ಇರ್ಲಿಕ್ಕಿಲ್ಲ, ಅನುಭವ ಇಲ್ವೇನ್ರಿ ಅವನಿಗೆ? ಇವೆಲ್ಲ ಇದ್ದು ಆರ್ ಎಮಿನೆಂಟ್ ಸ್ಕಾಲರ್ ಅನ್ನುವಂಥ ಒಂದು ಆಯ್ಕೆ ಸಂದರ್ಭದಲ್ಲಿ ಒಂದು ಅವಕಾಶ ಇದೆ. ಯಾವ್ಯಾವ ಕ್ಷೇತ್ರದಲ್ಲಿ ಎಮಿನೆಂಟ್ ಸ್ಕಾಲರ್ಗಳದಾರೋ, ಜಾತಿ, ಮತ, ಪಂಥ, ಲಿಂಗ ಇವ್ಯಾವ ಭೇದಗಳನ್ನು ಎನಿಸದೆ, ಲೆಕ್ಕ ಹಾಕದೆ ಅವೆಲ್ಲವನ್ನು ಕಳೆದರವರು. ಕೆಲವರು ಬರೀ ಪಾಸಿಟಿವ್ ಆಗಿರುವವನ್ನು ಕೂಡಿಸ್ತಿರ್ತಾರೆ. ವಾಲಿಕರ್ ಅವರು ಕೂಡಿಸಬಲ್ಲರು, ಕಳೆಯಬಲ್ಲರು, ಗುಣಿಸಬಲ್ಲರು, ಸಂದರ್ಭ ಬಂದರೆ ಭಾಗಿಸಲೂ ಬಲ್ಲರವರು. ಯಾಕಂತ ಹೇಳಿದರೆ ಅವರೊಬ್ಬ ಗಣಿತ ಶಾಸ್ತ್ರಜ್ಞರು. ಇದನ್ನೆಲ್ಲ ಮಾಡಿದರೆ ಅವರು ಕೂಡಿಸಿದ್ರು, ಕಳೆದ್ರು, ಗುಣಿಸಿದ್ರು, ಸಂದರ್ಭ ಬಂದಾಗ ಅದನ್ನು ಭಾಗಿಸಿದ್ರು. ಹೀಗೆ ಮಾಡುವುದರ ಮೂಲಕ ವಿಶ್ವವಿದ್ಯಾಲಯದಲ್ಲಿ ಒಂದು ಸಮಾನತೆಯನ್ನು ತಂದುಕೊಡಬೇಕನ್ನುವಂಥ ಕಾರಣಕ್ಕಾಗಿ ಕೆಲಸ ಮಾಡಿದ್ದಂಥದ್ದು ಕೆಲವರಿಗೆ ನೋವನಿಸ್ತು. ಯಾರ್ಯಾರನ್ನೋ ವಿಶ್ವವಿದ್ಯಾಲಯಕ್ಕೆ ಎಲ್ಲೋ ಕಾಡಿನಲ್ಲೋ, ಬೆಟ್ಟದಲ್ಲೋ, ಗುಡ್ಡದಲ್ಲೋ ಕುರಿ ಕಾಯುವ ಒಬ್ಬ ಹುಡುಗ ಈ ವಿಶ್ವವಿದ್ಯಾಲಯದ ಕುಲಪತಿ ಆದನಲ್ಲ ಅನ್ನುವುದಂಥದ್ದನ್ನು ನುಂಗಲಾರದ ತುತ್ತಾದಂಥ ಸಂದರ್ಭದಲ್ಲಿ, ಯಾವುದೋ ಗುಡ್ಡದಲ್ಲಿ, ಎಲ್ಲೋ ಅಡವಿಯಲ್ಲಿ ಕುರಿಗಳ ಹಿಂದೆ ತಿರುಗುವ ಮನುಷ್ಯ ವಿಶ್ವವಿದ್ಯಾಲಯದ ಕುಲಪತಿ ಆದನಲ್ರಿ. ಈ ಮಾತು ಎಲ್ಲರಿಗೂ ಅನುಭವಿಸುವುದಿಲ್ಲ. ಕೆಲವು ಮೂಲಭೂತವಾದ ಮನಸ್ಸುಗಳಿವೆಯಲ್ಲ, ಮೂಲಭೂತವಾದಂಥ ಮನಸ್ಸುಗಳು ಎಲ್ಲ ಸಮಾಜದಲ್ಲೂ ಎಲ್ಲ ಕಾಲಕ್ಕೂ 25% ಇದ್ದೇ ಇರ್ತಾವೆ. ಇಲ್ಲ 10%, 1% ಅಂತೂ ಇದ್ದೇ ಇರ್ತದೆ. ಅಂತಹ ಮೂಲಭೂತವಾದ ಮನಸ್ಸುಗಳು ಅಸಹನೆ ವಾಲಿಕಾರ್ ಅವರನ್ನ ಎಲ್ಲಿಗೋ ಕಳಿಸ್ಬಿಡ್ತು. ಆದರೆ ಯಾರು ಸಾಕ್ರೆಟಿಸ್ ಆಗಿರ್ಬೋದು, ಬುದ್ಧ ಆಗಿರ್ಬೋದು, ಗಾಂಧಿ ಆಗಿರ್ಬೋದು, ಅಂಬೇಡ್ಕರ್ ಆಗಿರ್ಬೋದು, ಬಸವಣ್ಣ ಆಗಿರ್ಬೋದು, ಇವರೆಲ್ಲ ಅಂತ ಹಿಂಸೆಯನ್ನು ಅನುಭವಿಸಿದ್ರೆ ಇವತ್ತು ತಂಪಿನಲ್ಲಿ ನೆನೆಯುವಂಥ ವ್ಯಕ್ತಿತ್ವಗಳವರೆಲ್ಲ ತಂಪತ್ತಿನಲ್ಲಿ. ಈ ವಿಶ್ವವಿದ್ಯಾಲಯದ ಮಾಡಿದ ಕೆಲಸಕ್ಕಾಗಿ ವಾಲಿಕಾರ್ ಅವರ ಹೆಸರನ್ನ ತಂಪತ್ತಿನಲ್ಲಿ ನೆನೆಯಬೇಕು ನಾವೆಲ್ಲ. ನಮ್ಮ ಮನೆಗೆ ಹೋದಾಗ, ದೀಪ ಹಚ್ಚುವಾಗ, ಊಟ ಮಾಡುವಾಗ ವಾಲಿಕಾರ್ ಅವರ ಹೆಸರನ್ನ ನೆನಪಿಸ್ಕೊಂಡು ನಾವು ದೀಪ ಹಚ್ಚಬೇಕು, ಊಟ ಮಾಡಬೇಕು. ನನ್ನಂತಮ ಎಲ್ಲೋ ಒಬ್ಬ ಚಮ್ಮಾರಿಕೆ ಮಾಡಿಕೊಂಡಿರ್ಬೇಕಾದಂಥ ಒಬ್ಬ ಚಮ್ಮಾರನ ಮಗ ವಿಶ್ವವಿದ್ಯಾಲಯ ಪ್ರಾಧ್ಯಾಪಕನಾಗಿ, ವಿಭಾಗದ ಮುಖ್ಯಸ್ಥನಾಗಿ, ವಿಶ್ವವಿದ್ಯಾಲಯದ ಕುಲಸಚಿವನಾಗಿ ಕೆಲಸ ಮಾಡ್ತಿದ್ದೀನಿ ಅಂತ ಹೇಳಿದರೆ ಅದರ ಹಿಂದೆ ವಾಲಿಕಾರ್ ಅವರ ಆಶೀರ್ವಾದ ಇದೆ. ನನ್ನಂತ ಅನೇಕ ಜನರಿಗೆ ಅಂತ ಆಶೀರ್ವಾದಗಿವೆ. ಇದು ಸತ್ಯ. ಹಾಗಾಗಿ ಪ್ರೊಫೆಸರ್ ವಾಲಿಕಾರ್ ಅವರು ಗಣಿತ ಶಾಸ್ತ್ರಜ್ಞರಾಗಿದ್ದರೂ ಕೂಡ ಈ ಲೋಕದ ಎಲ್ಲ ಕ್ಷೇತ್ರಗಳ ಜ್ಞಾನದೊಂದಿಗೆ ತಮ್ಮ ಜ್ಞಾನವನ್ನು ಕೂಡಿಸಬಲ್ಲರು, ಕಳೆಯಬಲ್ಲರು, ಗುಣಿಸಬಲ್ಲರು, ಸಂದರ್ಭ ಬಂದರೆ ಅದನ್ನು ಭಾಗಿಸಲಬಲ್ಲರು. ಅಂಥ ವಿದ್ವತ್ತು, ಪ್ರತಿಭೆ, ಶಕ್ತಿ ನಾವು ವಾಲಿಕಾರ್ ಅವರಲ್ಲಿ ಕಂಡಿದ್ದೇವೆ. ಇಂಥ ಲೆಕ್ಕಾಚಾರವನ್ನು ಅವ್ರ ಜೀವನದಲ್ಲಿ ನಿರಂತರವಾಗಿ ಕೂಡಿಸ್ತಾ, ಕಳೆಯುತ್ತಾ, ಗುಣಿಸುತ್ತಾ, ಭಾಗಿಸುತ್ತಾ ಬಂದಂಥ ವಾಲಿಕಾರ್ ಅವರಿಗೆ ಇವತ್ತ ಅಮೃತ ಮಹೋತ್ಸವದ ಗಳಿಗೆ ಕೂಡಿ ಬಂದಿದೆ. 100 ವರ್ಷಗಳು ಶತಾಯುಷಾಗಿ ಬಾಳಲಿ ಎನ್ನುವಂಥ ಹೆಬ್ಬೈಕೆ ಹಿರಿದಾದಂಥ ಈ ಸಂದರ್ಭದಲ್ಲಿ ವಾಲಿಕಾರ್ ಅವರು 100 ವರ್ಷಗಳು ಅವರು ಯಶಸ್ವಿಯಾಗಿ ಬದುಕುವಂತಾಗಲಿ. ಖಂಡಿತವಾಗಲೂ ಅವ್ರು 100 ವರ್ಷಗಳಕ್ಕೆ ಅದಕ್ಕಿಂತ ಆಚೆ, ಯಾಕಂತ ಅವರು ಹೇಳಿದಾಗೆ ಅಮ್ಮಾರು ನಮ್ಮ ಒಲಿ ಸರಿ ಇದೆ ಅಂತ ಹೇಳಿದ್ರಲ್ಲ, ಅದು ಸರಿ ಇದ್ರೆ ಆರೋಗ್ಯ ಸರಿ ಇರ್ತೈತೆ ಅನ್ನುವಂಥ ಮಾತನ್ನು ಅವರು ಈ ನಮ್ಮೆಲ್ಲರ ಮಧ್ಯದಲ್ಲಿ ಮತ್ತೆ ನಾವೆಲ್ಲರೂ 75 ವರ್ಷ ಅಲ್ಲ, ಅವರ 100 ವರ್ಷದ ಸಂಭ್ರಮಾಚರಣೆಯಲ್ಲಿ ನಾವೆಲ್ಲ ಪಾಲ್ಗೊಳ್ಳುವಂತಾಗಲಿ ಅನ್ನುವಂಥ ಹಾರೈಕೆಯ ಮಾತುಗಳನ್ನು ಇಲ್ಲಿ ಹೇಳ್ತಾ, ಇಂಥದ್ದೊಂದು ದೊಡ್ಡ ಅವಕಾಶವನ್ನು ಕೊಟ್ಟು ನನಗೆ ಮಾತನಾಡಲಿಕ್ಕೆ ಅವಕಾಶವನ್ನು ಕೊಟ್ಟಿದ್ದಕ್ಕಾಗಿ ಮತ್ತು ನನ್ನ ಮಾತುಗಳನ್ನು ಯಾರ್ಯಾರಿಗೆ ಹೇಗೆ ಅನಿಸ್ಯಾವೋ ಲೋಕೋ ಭಿನ್ನ ರುಚಿ ಎನ್ನುವಂಥ ಒಂದು ಮಾತಿದೆ. ಅದು ಯಾರಿಗೆ ಏನನ್ನಿಸಲಿ, ನನ್ನ ಮಾತುಗಳು ವಾಲಿಕರ್ ಅವರನ್ನು ಕುರಿತಾಡಿದಂಥ ಮಾತುಗಳು ಸರಿ ಇವೆ ಎನ್ನುವಂಥ ಆತ್ಮತೃಪ್ತಿ ನನಗಿದೆ ಅಂತ ಹೇಳ್ತಾ ನನ್ನ ಮಾತುಗಳನ್ನು ಮುಗಿಸ್ತೀನಿ. ನಮಸ್ಕಾರಗಳು.
Thank you, sir. Gratitude is the closest thing to beauty manifested in an emotion. Now, I have the honor of inviting Professor Sridevi Madam to propose vote of thanks.
Dignitaries on the dais and off the dais, I am here to propose vote of thanks on behalf of Department of Mathematics in association with the Paute Institute of Mathematical Sciences, Department of Computer Science and Department of Statistics, and on behalf of organizing team of National Conference organized in honor of Professor H.B. Walikar, former Vice Chancellor, Karnataka University, Dharwad, on his 75th birthday. First of all, I would like to thank President of this function, Professor N.Y. Mattihal, Registrar Evaluation, Karnataka University, for presiding over this function and for being with us. Thank you, sir. I would also thank today's chief guest, Professor M.M. Shikre, General Secretary, Indian Mathematical Society, Emirate Professor, JSPM University, Pune, for gracing the occasion. Thank you, sir. I would like to offer a special thanks to Professor H.B. Walikar, former Vice Chancellor, Karnataka University, for accepting our invitation to be with us and also for accepting our gesture to organize this event. Thank you, sir. I also thank Ansuya Walikar, Madam, special thanks are due to Professor A.B. Vedamurthy, President, Karnataka University PG Teachers Association, and Senior Professor, Department of Biotechnology and Microbiology, Karnataka University, Dharwad. I take this opportunity to thank all our syndicate members for gracing the function. I would like to thank Professor R.R. Hampiholi, Professor, Department of Mathematics, Anuvartik Mirji, Bhartesh Institute of Technology, Belgavi, and also Vice President of Professor H.B. Walikar Felicitation Committee, the Treasurer, Professor H.S. Ramane, Organizing Secretary, Professor Subhash Natikar, Chairman and PIMS Director, Professor S.C. Shiral Shetty, and Professor Nagesh, Chairman, Department of Statistics, in organizing this national conference in the most befitting academic manner. I also thank all the donors, well-wishers of Professor H.B. Walikar for generously organizing this academic event. I would also thank wholeheartedly the family members of Professor Walikar sir and generously helping us in organizing this mega event and also for attending this program. I thank all the invited speakers, resource persons, for accepting our invitation and come over here. I thank media personnel for both print and electronic for giving a good coverage of this academic program. I must also thank all our research scholars, teaching assistants, PG students of the 3 departments for working tirelessly in organizing such a systematic mega academic event. I also thank both teaching and non-teaching fraternity for making this program a grand success. Thank you one and all.
ಇವು ಚೇರ್ ತೆಗೆದ್ರೆ ಅರೇಂಜ್ ಮಾಡ್ಬೇಕು. ಇವತ್ತಿನ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಒಂದು ಸ್ಲೈಟ್ ಬದಲಾವಣೆ. ಈಗ ಕೀನೋಟ್ ಅಡ್ರೆಸ್ ಮುಗಿದ ತಕ್ಷಣ ಲಂಚ್ ಮುಗಿದ ತಕ್ಷಣ ಪ್ಯಾರಲಲ್ ಸೆಷನ್ಸ್ ಎಲ್ಲ ಈಕ್ವಲ್ ಆಗಿ ನಡೀತಾವೆ. ನಾವು ಮೊದಲು ಕೀನೋಟ್ ಮುಗಿದ ತಕ್ಷಣ ಪ್ಯಾರಲಲ್ ಸೆಷನ್ ಮಾಡಿ ಲಂಚಿಗೆ ಬರಬೇಕಾಗಿತ್ತು. ಈಗ ಲಂಚ್ ಮಾಡ್ಕೊಂಡು ಪ್ಯಾರಲಲ್ ಸೆಷನ್ ಸ್ಟಾರ್ಟ್ ಮಾಡೋಣ. ಹಾಗೆ ಮಾಡ್ರಿ. Now keynote address by Professor M.M. Shikare. ಸ್ವಲ್ಪ
Formal function, thank you.
ಹೇಳಿ.
On that note, we conclude the formal function with the words Shanai Pantha, Shanai Kantha, Shanai Parvatamastake, Shanai Vidya, Shanai Vityam, Panchahetani, Shanai Shanai. Thank you.
Professor Narayan Swami, please come on the desk. Now I request Professor N.M. Buzurge sir to chair the session. Professor Busnurmar sir and Professor Buzurge sir, please come on the desk to chair the session. ಸೆಷನ್ ಚೇರ್ ಆದ್ಮ್ಯಾಗ ನೀವು ಅವ್ರಿಗೆ ಥ್ಯಾಂಕ್ಸ್ ಹೇಳಿ. ಸೆಷನ್ ಚೇರ್ ಆದವ್ರಿಗೆ ಈಗ ಹೇಳ್ಬೇಕು, ಆಮೇಲೆ ಅವ್ರು ಸೆಷನ್ ಚೇರ್ ಮುಗಿದ್ಮ್ಯಾಗ ನಾ ವೆಲ್ಕಮ್ ಮಾಡೀನಿ, ನೀವು ಥ್ಯಾಂಕ್ಸ್ ಹೇಳಿ. ಇವ್ರಿಗೆ ಸ್ಟಾರ್ಟ್ ಮಾಡತ್ತ ಹೇಳಿ, ಸ್ಟಾರ್ಟ್ ಮಾಡಿ. Half an hour, 30 minutes, 30 to 45 minutes. We shall start lunch. Sir,
ये है क्या पॉइंटर?
ಲಕ್ಷ್ಮೀ ಸರಿ ಕರ್ಕೊಂಡ್ಬರೋ, ಟೈಮ್ ಆಗಿತ್ತು. ಕರ್ಕೊಂಬ ಬರ್ಲಿ ಬಾ, ಇಲ್ಲಿ ಬರ್ತಾರ ಬಾ, ಕರ್ಕೊಂಬ. ಕೊಡ್ರಿ. ಕ್ವಶನ್ ಮಾಡ್ಸಕ್ಕೆ ಆಯ್ತು ಕರ್ಕೊಂಬಂದು ಕೊಡ್ತೀರಿ ಒಟ್ಟು. ಇದು ನೋಡ್ರಿ ಇಲ್ಲೇ ಸ್ಟೇಜ್ ಬಂದು ಆಮೇಲೆ ಥ್ಯಾಂಕ್ಸ್ ಫಾರ್ ಶೇರಿಂಗ್ ದಿ ಸೆಷನ್. ಕೊಡ್ತಾರೆ ನೀವು ಅಲ್ಲೇ ಬಂದು ಕೂಡ ನೀವು ಅಲ್ಲೇ ಕೂಡ
Yes. Today, Professor is talking about path eigenvalues and path energy of graph. And I'm sure all are familiar with eigenvalues, whether in graph theory or somewhere else. I wish it will be a very interesting talk. I request Professor Sikare to give his talk.
Okay, should I start? Okay, Professor Bujurge, Professor Basnor Mat, and friends. So, as already announced, this is a technical talk, and the topic on which the talk is being given has been mentioned, because most of you are familiar with spectral graph theory. So I chose this topic, whose title is Path Eigenvalues and Path Energy of Graphs. So in 2016, 2017, we introduced the idea of path matrix of a graph. You know that efficiency matrix of a graph is very well known, you know that. How do you define the adjacency matrix of a graph? If G is a graph with n vertices, we associate a graph of size n by n, where ijth entry is 1 if the corresponding vertices are adjacent, otherwise it is 0. There is another notation, and then the spectral graph theory is related about the adjacency matrices. People evaluate the eigenvalues of adjacency matrices, spectrum of the adjacency matrices, energy of the adjacency matrices, and all other things. And then there is another kind of the graph, very famous, distance matrices, where ijth entry is the distance between two corresponding vertices. So, and then people investigate their properties, eigenvalue spectrum. Now, in 2016-2017, we defined a different type of matrix, so which we called a path matrix. And that time we did not realize how much it will go up. Because when you introduce the concept, you do not know how it will be reflected, how other people will be working on it. But we have noticed that during the last 6-7 years, 31 papers have been written on that paper. So we are excited, and I thought that I should introduce the basic concept and the others' contribution on this subject. More and more people are working on this. So I would like to introduce what is that matrix. We define a different type of matrix, that is one thing, which we call path matrix. Then we investigated their eigenvalues, energy, and we would like to take the review of the mathematician, international mathematician, who have contributed on this paper. We have written more papers. We have extended these topics. So let us go to the definition of a path matrix. And as I said that the definition was given in 2016-17. Gutman contributed with it. We wrote an article with Gutman. The paper appeared in Match. Plus, earlier slide. Yeah. In 2018, it appeared. And then we defined the path matrix. So if G is a graph with n vertices, whose vertex it is V1, V2, Vn. Then we associate a matrix denoted PG, like adjacency matrix AG. Here we use the word notation PG, and whose entries are Pij. Ijth entry is Pij, and ijth entry, that means the entry corresponding to Vij, Vj, is the maximum number of vertex disjoint paths between Vi and Vj. And that means for if I is not equal to j, Pij is the maximum number of vertex disjoint paths between Vi and Vj. And when I is equal to g, that means diagonal entries, they are 0. So this matrix PG is known as a path matrix. And its eigenvalues, to distinguish it from the ordinary eigenvalues, because eigenvalues of adjacency matrix, they will be known as, or they will be called as ordinary eigenvalues. For this matrix, the eigenvalues of PG will be called as path eigenvalues to distinguish them from the ordinary or eigenvalues of the adjacency matrix. Next. So it says that the path eigenvalues, your graph is of order n. So the path eigenvalues, which we call lambda 1, lambda 2, lambda n. And from linear algebra, you know that if you have a matrix of size n, its eigenvalues are found from the characteristic equation. If a matrix has size n, its characteristic polynomial of order degree n. And if the degree of the polynomial is n, the fundamental theorem of algebra says that it has n roots. So if original graph is of size n, it has n eigenvalues, which we denote lambda 1, lambda 2, lambda n, and they are the roots of the characteristic polynomial of Pg. And the second property says that Pg is real and symmetric. Real because number of maximum paths will be a real number. In fact, it is an integer, so real number. And it is symmetric the number of paths between Vi and Vj is same as number of paths between Vj and Vi. So it is symmetric. And linear algebra result says that if the graph is real and symmetric, its eigenvalues are all real. And then sum of the eigenvalues, diagonal entries are 0. You know that the sum of the eigenvalues is equal to trace of the matrix. Trace is the sum of the diagonal entries, which is 0. So it says that if we add up all the eigenvalues of the path matrix, its sum will be 0. And finally, we talk about the maximum eigenvalues of PG. Maximum eigenvalues of AG is called the spectral radius. So here maximum eigenvalue of PG will be called as path spectral radius. So there will be, to distinguish it from spectral radius, we call it as path spectral radius. Next, some remarks. As I said, people, after publishing this paper, when it is published, people have tried to study it and try to prove more general results. So here it is, first remark says that maximum number of vertex disjoint paths, we call it because we did not know what it is called, but it is already mentioned, some mathematicians, that it is called connectivity between Vi and Vj. In 2002, Beinecke, Wollerman and Poppet, they are very popular mathematicians. So they called that average degree of Z in this paper, and this maximum number of paths between Vi and Vj, they define it to be connectivity between I and Vj. So the path matrix is also called as connectivity matrix in some papers. And the second one is another person, we call it as the largest eigenvalue of PG as the path spectral radius. But someone else, it's called the path index of the graph. That depends on the people in which context they are working and in which definition, in which terminology or which result they are proving. So in one paper, which is authored by Zhu and Zhao, the paper has been published in the journal in 2024. They call this path, we call it as a path spectral radius, they call it path index, and they prove various properties of this. And the third remark says that the eigenvalues of the adjacency matrix AG, as I said that I have already recalled the definition of AG, adjacency matrix, they will be called as ordinary eigenvalues because sometimes you will be comparing their eigenvalues. Eigenvalues of AG and eigenvalue of PG. So to distinguish them from the path values, the original eigenvalues or the eigenvalues of AG will be called as ordinary eigenvalues of these. Okay, so here is an example. A graph and its path matrix. So we have a graph with 7 vertices. We have the picture. 7 vertices are labeled from 1 to 7. So its path matrix will be of size 7 by 7. So rows will be labeled as 1 to 7. Columns will be labeled as 1 to 7. So first entry, 1, 1 entry is 0 because there is no path from 1 to 1. So that is 0. The next entry in the first row, second column is 2 because that comes from the maximum number of paths from 1 to 2. 1 and 2 lies in a triangle. So you can say that there are 2 paths. One is the edge 1, 2 and the other path is 1, 3, 2. These are the only 2 vertex disjoint paths. So the entry is 2. So all the entries have been written and the matrix PG has been found. The next thing is we would like to find out is path eigenvalues. That means the eigenvalues of PG. So how do you find? As already you write the characteristic polynomial which will be of degree 7. If you solve the roots of this, there will be 7 eigenvalues And we have here. Next. Yeah. So if you find the eigenvalues of PG, now a polynomial rubric receiver, how to do it? You can do it with the help of the computer, computational techniques. And then we found that the spectrum of P, spectrum of G is the set of all eigenvalues. The largest eigenvalue is 9.11 and the rest of the eigenvalues have been written in the first bracket. And we would like to compare it with the ordinary eigenvalues, so which we call the spectrum of G. So the spectrum of G has again 7 eigenvalues. The values have been written. And you can notice that the largest path eigenvalue is 9 point something, whereas the largest ordinary eigenvalue is 2.9. So from that we say that path spectral radius of G, largest path eigenvalue, that is 9 point rho G, we denote 9.1136, while the spectral radius of G, the largest ordinary eigenvalue is 2.92. This is just, you compare between the two eigenvalues and compare between the spectral radii. Next. We would like to harness some properties of some path eigenvalues. So here we consider spectrum of disconnected graph. We consider the disconnected graph with two components. Component means is a connected graph, maximal connected graph. Another component is maximal connected graph. So if you have one vertex from the first component and another vertex from the other component, there is no path. That means the number of paths will be 0. So considering this fact, if you have a graph with two components, then its path matrix will have this form. Diagonal forms will be the entries current path matrix of G1, path matrix of G2, and the other entries will be 0. So zeros are the zero matrices of appropriate size. And therefore, if you have a graph with two components, its spectrum, path spectrum of G, will be the union of path spectrum of G1 and path spectrum of G2. You can extend this idea, and if you have a disconnected graph with n components, components being G1, G2, Gn, then PG, the path graph of this graph, path matrix of this graph, will have the form where the diagonal structure is the path matrix of G1, first component, then path matrix of G2, second component, and so on. So path matrix of GP, because there are P component, and the other entries are 0. So zeros are zero matrices of C. And then from linear algebra, we can say that the path spectrum of, in this case, will be the unions of path spectrums of G1, G2, GP, and so on. Some proposition, you know that. So simple proposition. So the one is, every integer, positive, 0 or negative integer, is path eigenvalue of some graph. So there are three possible. The proof says that if you consider integer, it could be 0, first value is 0, then what is the graph corresponding to that? So for, if k is an integer and k is equal to 0, you look at null graph, a graph with no edges. And a graph with no edges has the eigenvalue as 0, one of the eigenvalue is 0. If k is positive integer, for example 2 or 3, or any integer, then you look at the tree with k plus 1, because a tree, path matrix of a tree and adjacency matrix of kn, they are equal. And adjacency matrix ordinary eigenvalues are n minus 1, minus 1, minus 1, minus 1. So if you have a tree with eigenvalue k, then you look at the tree with k plus 1 eigenvalues. tree with k plus 1 vertices. And then if you find out its eigenvalues, path eigenvalues, a tree with k plus 1 vertices will have the eigenvalues k, then minus 1, minus 1, minus 1, n minus 1 time. And finally, if the integer is negative, k is equal to minus h, where h is positive, then you look at the complete bipartite graph KHH, then this complete bipartite graph with HH vertices has one of the values, eigenvalues has minuses. So you consider any of the type integer, then you can have the graph whose path eigenvalue is the corresponding integer. Then some properties of PG, general properties of the path matrix. So I assume that if G is a connected graph which has vertices at least 2 and P be the corresponding path matrix, I write P or PG, one and the, because sometimes it comes PG, sometimes it comes P. Following statements hold. P is irreducible, means then another property is P has path eigenvalue rho g, which is positive. And there is an associated vector. So these properties come from the linear algebra. Because you know in linear algebra, a matrix is said to be irreducible if it cannot have a upper block triangular form, you know that. So this P matrix, path matrix have that property. Then there is a one eigenvalue which is positive and the corresponding eigenvector is denoted by x, that is positive. And as already we found that this value is known as path spectral radius. Then the third property, if you take any eigenvalues of P, then it lies between minus rho and rho, where rho is the largest eigenvalue. And then fourth property says that if you use any eigenvector, you can express u in terms of x. X is already mentioned that there is a positive eigenvalue, rho, and there is a positive, the corresponding vector is x. So the fourth property says that if u is any eigenvector for P that correspond to rho, then u or any eigenvector you can write in terms of x by multiple of alpha. So these properties follow from the linear algebra technique. Then some more properties, that is about one matrix being greater than the other. So the definition is if you have two matrices A and B, A, Aij, B, Bij, then we say that A is greater or equal to B. If the corresponding entries of A, they are greater than the corresponding entries of B. That means Aij is greater or equal to Bij. And if there is at least one entry in Aij which is greater than the corresponding entry in Bij, then we say that A is strictly greater than B. So with this assumption, when two matrices of same size are given, we say that A is strictly greater than B or A is greater or equal to B. So with this understanding, we have the theorem now. So G is a graph and Vi and Vj is the pair of vertices that is not adjacent. And then we add the age between Vi and Vj and get a new graph, which we call G plus Eij, where Eij is the age between Vi and Vj. Is a graph obtained by adding an age between Vi and Vj. And then what is the relation between the original graph, new graph? New graph, Vi and Vj were not adjacent. You are making them adjacent and getting the new graph. So we would like to consider path matrix of the original graph and the path matrix of the new graph, namely P of G plus Eij and Pg. And you can notice that Pg plus Eij is strictly greater than Pg because the number of paths between Vi and Vj is increasing by 1. Whatever where the number of paths between Vi and Vj, you are adding one vertex, one edge between the. So you are increasing the number of paths from Vi to Vj by 1. So that int is strictly greater than the corresponding int in the earlier graph. So P of G plus Eij is strictly greater than Pg. And hence, spectral radius of new graph is strictly greater than the spectral radius of the original graph. And the corresponding, the special cases, if G is a connected graph of order n, then in fact we write the inequality that the spectral radius of G is greater than equal to n minus 1. And the equality holds in this inequality if and only if G is a tree of order n. So this gives the lower bound for the spectral radius. If you have a graph with n vertices, what is the lower bound for the spectral radius? So this is the lower bound. It says that if G is any connected graph on n vertices, lower bound, the spectral radius is always greater or equal to n minus 1. And we give the condition when the equality holds. Similarly, we give the upper bound for the spectral radius by the second result. When G is any connected graph on n vertices, rho of G spectral radius, path spectral radius of G is always less equal to n minus 1 square. And the equality holds for upper limit or upper bound is when G is equal to Kn or complete graph in n vertices, you can notice that the spectral radius is n minus 1 square. Then there is a proposition, if G is a K connected graph on 2K plus 1 vertices, then we give the interval which contains the spectral radius. So the result says that the path spectral radius of G lies in the interval 4k square plus. For example, if you have a 3 connected graph on 7 vertices, k is equal to 3. So you have a 3 connected graph on 7 vertices. Then the path spectral radius of G will lie between 12 and 4 into 3 square, 12 and 36. So depending on the value of k, we can identify the interval which contains the spectral radius. Then we would like to consider or obtain the spectral radius and the eigenvalues, path eigenvalues of some special types of graphs, namely unicyclic graphs, bicyclic graphs. So here is one operation which is already studied by mathematicians, pruning operation. So what it says that if you have a graph G and if you have pendant vertices, delete the pendant vertices. When you delete one pendant vertices, the corresponding edge will be deleted. So if you have a graph G, delete all the pendant vertices. You get the new graph, which is called a pruning of the earlier pruning operation. If there are again pendant vertices, then you remove them. And finally, you get a graph which is PR star, pruning. If it comes in the first step, we just denote by PR. And still if there are more pendant vertices, you continue the process till all the pendant vertices be eliminated. And you get one graph, PR star. Now original graph G and the new graph PR star, what is the relation between their path matrix? So it says that the path matrix of G is equal to path matrix of the final graph, PR star G. That one is a matrix of appropriate dimension whose entries are 1. Then 1 and J n minus 1. J is a matrix whose all entries are 1 and its size is n minus n star because the n star has already been identified in the upper one. So this gives the relation between, you have the graph G, you make the pruning operation, you get the final graph, and then you study the relation between path graphs of this or path matrices of this graph, and then go to the next. Path spectral radius of unicyclic graph. Unicyclic graph, that means graph with one cycle. Unicyclic itself indicates that graphs with one cycle. So we denote by Cp the cycle of length p. No problem in that. C3 cycle of length 3. C10 cycle of length something like. Then we denote by Un the set of all connected unicyclic graphs with n vertices. Unicyclic graph may be connected, may be disconnected. So we identify the connected unique cyclic graph. So the cycle will be there and the other edges, other structure will be there, which is attached to the cycle. So Un set up all connected unicyclic graphs on n vertices. And again from the n vertices graphs, we identify, suppose we have n is equal to 10. So we have U10, all unicyclic graphs on 10 vertices. So cycle may be of length 3, it will contain cycles of length 4, vertices will be 10, but cycle will be of 3 size, some will be of size 4, some cycle size will be 5, some of the cycles will be of size 7, something like that. So from Un, we identify cycles of length k, cycles of size k. So that is denoted by, so in addition, Unk be the subset of Un, consisting of graphs whose cycle is of size 10. So if you have n is equal to 10 and k is equal to 6, U10 6 means all unicyclic graphs on 10 vertices, each of which has a cycle 6, like that. So k changes, length of the cycle changes, n remains fixed, right? So first proposition. So these propositions in our lecture, this proposition is where we put as a conjecture, because we are not able to, even Gutman, we were not able to prove. So they were mentioned as a conjecture, but somebody else did it. So that becomes the proposition. So if G belongs to UNK is the set of unicyclic graphs on n vertices, all where cycle is of length psi. Then spectral radius of G depends only on parameters n and k. It depends on, and for fixed n, as I say, n is equal to 10, and we vary k is equal to 3, k is equal to 4, k is equal to 6. So rho G is monotonically increasing function of k. If you have cycle, 10 vertices, cycle length 4. 10 vertices, cycle 5. So cycle 5 will have the large. If you have the cycle length 6, it will have the spectral radius greater. Second proposition, G is unicyclic graph on n vertices. Then spectral radius, path spectral radius is maximal. If and only G is isomorphic to cycle of length n. Because on 10 vertices, connected graph with one cycle, you can have a cycle of length 10, then you have a cycle of length 1 with one edge, or you can have a cycle of length 8 with 2 edges. So here, the path spectral radius is maximal if and only G is isomorphic to Cn. And the third property, if G belongs to UNK, unicyclic graph on 10 vertices where every graph has cycle of length k, then path spectral radius is minimal if and only you apply the pruning operation on G and you get a graph which has no pendant vertices. So pruning of G is isomorphic to the smaller cycle of length 3. You may have n is equal to 20 and k is equal to 7. Then rho G is minimal if and only you go on doing the pruning, and finally the minimal value or the graph that you are getting pruning of G is isomorphic to C3. Bicyclic graphs. So what we did earlier, we have found spectral radius, some classes of unicyclic graph. Now you consider bicyclic graph. Bi means 2. Graphs with 2 cycles. So the question is, how many types of, how the bicyclic graph look like? What are the types? So we do the definition, but from the picture, you can notice the type of the bicyclic graph. So there are three types of graph. One is the first type. There are two cycles and they are joined by the path. So if the first cycle A has number of vertices A, another cycle has number of vertices B, and the path has vertices C. Then second type, two cycles have just one vertex common. And the third type of the graph, that two cycles have a path in common. So you take any or draw any bicycle graph, it will be in one of the three classes. And then we denote it by first type of graph B1 ABC. Second type B to the power 2 in bracket. And third type of graph notation B to the power in bracket 3. Some properties here. First type of graph, we count the number of vertices. Number of vertices in A plus B, vertices in cycle 2, and the number of vertices in path. So A plus B. Then second type, when two cycles have a vertex in common, number of vertices A plus B minus we can, because that common vertex is counted too. And for third, when two cycles have a path in common, then the number of vertices is A plus B minus C minus 2, where AB is greater or equal to 3 and C is positive. And then some notations for I is equal to 1, 2, 3, we denote by script B to the power I. Again, I is equal to, there are three types of it. So B to the power I, the set of all connected bicyclic graph without pendant vertices of type BI. So B, simple B, capital B, I is equal to 2 for example. Then script B to the power 2, what it would be? Set of all connected bicyclic graphs of type 2. And if I is equal to 1, script B to the power 1 will be connected graphs of type 1 without pendant vertices. And finally, denote by B suffix n, Bn, the set of connected bicyclic graphs with n vertices. So these graphs may come from the first type. Then the elements of Bn, they may come from the second type, or they may come from the third type. For example, B4, they will be the connected bicyclic graphs with 4 vertices. Some may come from the first graph, second of the type, third from type. They are clubbed together and B4 is obtained. Now propositions. Again, these were conjectures in earlier thing. So, proposition. If G belongs to Bn, G is a connected bicyclic graph with n vertices. Then spectral radius, of course, path spectral radius is maximal. If and only if G belongs to the third type. Because Bn, as I already pointed, they may consider graphs from first type, second type, third type. We want rho G to be maximal. So, maximality is obtained when the graph G belongs to B3. That means that graph is of type 3 and here n, number of vertices is B plus C minus 2, where AB is greater or equal to 3 and C is positive. And the last proposition, if G is a bicyclic graph with n vertices, then we find another extremal value. That means path spectral radius to be minimal if and only if pruning of the graph is isomorphic to the graph of type 2 with 3, 3. A is equal to 3, B is equal to 3. Note that second type is AB. A stands for a cycle with 3 vertices. B stands for a cycle with 3 vertices and they have a common graph. So B233 is a graph consisting of 2 cycles having 1 vertex in common. So here we just find out larger spectral radius when G is a bicyclic graph with n vertices. We find out maximal spectral radius, minimal spectral radius in for Bn. Path energy of graphs. You already know the ordinary energy of the graph. Ordinary energy is the absolute values of ordinary eigenvalues of the graph. This is known. If AG, adjacency matrix, you find out its eigenvalues, ordinary eigenvalues, you take the absolute values, add up them, you get ordinary energy of the graph. Guttman defined it in 1980. Now this is path energy. So we have the graph, we have the path matrix, we find the eigenvalues and take their absolute values, add up it. Whatever you get, that will be the path energy of the graph. So we will be having two energies. One is ordinary energy, other is path energy for a given graph. Extremal values of path energy carried out by Illich and Basic. So as I said, several people are working on this topic. So Illich and Basic, they wrote a paper that appeared in the journal, name of the journal is given. And it was written in 2019. Our paper appeared in 2018. They published the paper in 2019. What they do is, they wrote a theorem, I write it a theorem. If G is a connected graph of order n, then path energy of graph, they gave the lower bound for the path energy of the graph. So they proved that PEG, that means path energy of the graph, is greater or equal to 2 times n minus 1. And the equality holds if and only if G is a tree of order n. It was a conjecture in our first paper. We wrote the first paper that published with Guttman in 2018. It was a conjecture. What was the conjecture? We just write the conjecture for a connected graph. Path energy is greater or equal to 2 into n minus 1. They proved it. You know that there is a difference between conjecture and a theorem. Conjecture is a statement which, when you verify with the example, it is true, for which no proof is given. But when the proof is given to the conjecture, it becomes a theorem. That happened here. And then the second one, they gave the upper bound for the path energy. So path energy of G is always less equal to 2 times n minus 1 square, with equality if and only if G is complete graph. And then in the theorem, they talk about the path energy of unicyclic. What we initially about, we talk about the spectral radius. We did not say anything about the path energy. They have given the bounds for the path energy of the unicyclic graph. So the theorem says that let G be a unicyclic graph order n. Then two results. Path energy of G, they give the upper bound for that. Path energy of G less equal to 4 times n minus 1. And the equality holds if and only if G is isomorphic to the cycle with n vertices. And then the lower bound of unicyclic graph. So the path energy of G is greater or equal to n plus under root n square plus minus 4n plus 20th. And the equality holds if and only if G is isomorphic to uniform graph UN3. Now what is UN3? We define the graph class UNK. That U should be script. UNK is the set of unicyclic graphs on n vertices where the size of the cycle is 3. So G should be isomorphic to graph with n vertices, unicyclic, and the cycle length is 3. And what they did is, Illich and Basic, they gave an efficient algorithm for computing the matrix PG. Now when you write the definition, you see Pij is the maximum number of vertex disjoint paths between Vi and Vj. Now given an ordinary graph, finding number of vertex disjoint path between Vi and Vj is a challenge. We never thought, we did not have idea. We just wrote the matrix and obtained some property. But there was a question, given an ordinary graph, how to find out all the paths, that means maximum number of paths between Vi and Vj which are vertex disjoint. But these people, they used only very old and deep result like Ford and Fulkerson algorithm, Menger's theorem. So using this Ford and Fulkerson's algorithm and Menger's theorem, they have given a systematic algorithm to compute the number of paths between any two vertices. So they give it in the theorem. Then another people in 2019, Akbari, Gutman and their team, they proved these results. Spectral radius of K-connected K-regular graph. That. So they proved that if G is a K-connected graph, K-regular graph with n vertices, then spectral radius maximum eigenvalue is K times n minus 1. K is connectivity and n is number of vertices. So spectral radius has been mentioned in terms of K and n, connectivity and number of vertices. And path energy of graph, they have actually given the number. The path energy of the graph, K connected graph, K regular graph is 2 times K into n minus 1. And then second theorem they proved is that for every Z belonging to n, again unicyclic graphs, you know that. Unicyclic graphs of order n, where the cycle size has length k, they proved that the path energy of Z is equal to 2 times n plus k minus 3, where the cycle size is greater equal to 3, but less equal to n minus 3. And it is equal to under root. So, P is equal to under root some quantity plus n plus k minus 3, where cycle c is n minus 2, or cycle size k lies between n minus 2 and n. So, path energy of Z is an increasing function of G. Another person, Hoffman, in his PhD thesis, obtained the following results. So, he considers graph G, which is K connected on n vertices. Then path energy of G is greater or equal to 2k n minus 1. So he obtained the path energy for K connected graphs. And then this bound equality holds if and only if G is uniformly K connected graphs. And further, he obtained the theorem that if G is a connected graph on n vertices and the degree sequence of G is given d1, d2, dn, then path energy of G, EPG, is less equal to, he gives the bound in terms of under root 2n, the sum of n minus I di square. So when the bound is given in terms of the degree sequence. So the path energy bound has been obtained in terms of degree sequence of the graph. Path energetic eigenvalues. Now, there are equi-energetic eigenvalues for ordinary. Now we define path energetic. That means two graphs, if they have the same path energy, we say that they are path equi-energetic graphs. Then we identify, obtain some pairs of path in equi-energetic graphs. So first theorem is that T is a tree on n vertices, then its path matrix is same as the adjacency matrix of Kn. And you know the eigenvalues of Akn, which is n minus 1, minus 1, minus 1, minus. So path eigenvalues of T and eigenvalues of Akn, they are same. So we conclude that the spectrum of path matrix for any tree is n minus 1, minus 1, minus 1. And its path energy, sum of the eigenvalues is 2 times n minus 1. And then we conclude that all n vertex trees are mutually path energic. And we write the corollary, if AP is an n vertex forest with C components, then path energy of the forest is 2 times n minus C. Nice regular graphs. So the definition of nice regular means it is a connected and its edge connectivity is equal to the degree of the graph. So they prove that nice regular graphs are equal energies. So the result says that R be a nice regular graph of order n and regular degrees R. Then path matrix of R is equal to R times adjacency matrix of Kn. And you know the adjacency matrix of Kn, its eigenvalues. So the spectrum of path matrix of any nice regular graph R is R times n minus 1, then minus R, because eigenvalues of Kn, they are n minus 1, minus 1, minus 1. And if we multiply by R, then the eigenvalues are multiplied by R. So you get the spectrum to be R, n minus 1, minus R, minus R. And path energy calculate to be 2R times n minus 1. So we conclude that all n vertex regular graph, nice regular graphs of degree R, they are all path equienergetic. And we draw this as a special case. If R is a n vertex regular graph of degree n with C components, all of which are nice, then path energy of R is equal to 2 times R, n minus C. H path matrix. Another version of, we talk about path matrix. Somebody else has generalized it. So the name of the authors we have generalized, Akbari and other people. They have defined new matrix, path matrix. So what they are doing is we write Pij, maximum number of vertex disjoint paths. What they do is maximum number of edge disjoint paths. So they just modify the condition and get a new matrix. And they study the properties of eigenvalues of that matrix, spectrum of those matrix. That matrix denoted by CG. So this matrix is not edge path matrix of Z. And the eigenvalues of this is known as S path eigenvalues of Z. And the energy is known as eighth path energy of the graph. So from the path energy, they go to the edge path energy. And here are some results. They proved this result. If Z is a graph on n vertices, then edge path matrix of Z, that is CZ, is equal to 2 times Jn minus In, where Jn is all one matrix of type n by n, and In is identity matrix of size 1. And second theorem says that if G is a graph of order n, and its edge path matrix has the form 2 times Jn minus In, then energy of CG, that means edge path energy of G, EC of G is less equal to 3 times n minus 1 upon 2. So they give the upper bound for this energy. And they write the conjecture, if G is a Eulerian graph, then prove that every entry of the CG is 1. So conjecture is a graph is Eulerian if and only every entry of CG is even. And this is the last but one slide, maybe. So you can say Hoffman again proved the following results. Now these earlier people introduced new graphs, edge path graph. So Hoffman proves the properties of this matrix. So lemma, he writes the lemma, P is the path connectivity matrix, which is called path matrix, and C is now edge path matrix. And then he says that C is greater or equal to P, because number of edge disjoint paths, vertex disjoint paths is much more than number of maximum. So C is always greater or equal to P. And then he gives another result that if G is K connected, LH connected graph on n vertices, minimum degree is small delta, and connectivity matrix has spectral radius rho 1. Each connectivity matrix has spectral radius gamma 1. Then the following inequalities hold. Is give the bound for path spectral radius, first inequality, that k times n minus 1 is less equal to rho 1 is less equal to 2 times number of edges of G minus delta. And the second inequality give the bounds for the spectral radius of CG. So it says that L times n minus 1 is less equal to gamma 1, less equal to 2 times number of edges minus delta 1. And then the bounds in the first inequality, the equality holds if and only if G is uniformly K connected. And second inequality holds in the first result if G is K regular and K connected. Whereas the second inequality comes, there are two inequalities. So the first inequality holds if G is uniformly L edge connected. And the second inequality holds if G is L regular and L edge connected. And there are references. I said that after we wrote our first paper in 2017, another 31 papers have been written on this. I just give the number of papers which have been written on our first paper. So 6 here, then 12, 19. So thank you very much. Yes.
Nice to. Am I audible? Okay. I was going through your slides. Okay. You have different prudent operations on pendants. Okay. Is this quasi partial order? Is this quasi partial order? Oh, okay. No, because every time you are pruning and then getting a graph and then. Right. Then if you have got resulting graph, is it C prime is less than or equal to C, kind of a thing?
You don't bother what is happening.
No, is it something like a graph minor operation? Okay. Because you said monotonically increasing kind of things are there. Okay. But your bipartite graphs are appearing. What about complete graphs? What about? Okay. That's fine. Thank you.
Hello. Sir, there are characterizations of graphs with respect to ordinary spectra. Ordinary spectra means adjacency matrix. With respect to bipartite graph, there are characterizations. If lambda is eigenvalue, minus lambda is also eigenvalue. Like that, many characterizations are there in ordinary spectra, like adjacency spectra. Are there attempts to make characterizations in this fashion in path spectra? माझा विचार असा आहे सर, ऑर्डिनरी स्पेक्ट्रा लाईक इफ देर इज अ eigenvalue lambda, there is eigenvalue minus lambda in bipartite graphs, which is true for trees also. So whether such a characterization is there in path eigenvalues, whether there are attempts already done?
Your matrix is changing.
Yeah.
You get n by n matrix. So what is happening, you know that for adjacency matrix, you are getting n by n side. Entries different. PG, you are getting n by n. The linear algebra tool says that if you have a matrix of size n, characteristic polynomial has degree n. So it has n roots. So whatever may be your graph, if the number of vertices is fixed, size of the matrix is fixed, degree of the polynomial is fixed, so the number of roots is fixed. Doesn't matter.
I asked whether in bipartite graphs there are roots. Whatever the number of positive roots are there, same number of negative roots will be there in ordinary spectra. Whether similar characterizations there in path spectra, I am asking. That I was asking. Because both are symmetric matrices like that. I did not see such a paper, that's why.
The question is, can both the spectra be same?
Like K12. K12, in ordinary graph, root 2 minus root 2, 0 are
T
there.
and Kn.
T and Kn.
Path of T is adjacency of T. Two different paths. One is path, other is complete. But path matrix of T is same as adjacency.
That is particular case. But here a lot of other characterizations there in...
What are other types of graphs which are equinegetic other than paths? That is question. That is open. You try for that.
Thank you, thank you.
Okay, thank you. Thank you once again. Haribo.
Yeah, right. You introduce this path matrix, right? And you write the eigenvalues. Okay. The question is basically path matrix is an operator. It has to operate on something which gives you some eigenvalues, right? But what is that operator on which this matrix, path matrix is operating? That is probably missing all over the talk. Because, it may give for each eigenvalue, you may get a matrix which may represent the eigenstate of that eigenvalue.
Yeah.
So that eigenstate is missing in your talk. Maybe my question is elementary, but one obtains the eigenvalues by treating this path matrix as an operator. Operating on which?
It is not an operation. It is different type of conditions.
How do you get the eigenvalues then?
Eigenvalues, I said, what is the matrix? Matrix of size n by n. If you have a graph, you start from the graph,
Right.
which has n vertices.
So this is a different way of getting the eigenvalues.
It is different way
not
of
operating on.
Before that, there are already established different ways of matrix. You know only adjacency matrix. But do you know that there is a adjacency, there is a distance matrix also? I'm telling you that.
But normally.
Distance matrix is also associated there.
Okay.
There's a Laplace matrix.
Okay.
So there are different types of matrices.
That way.
So similarly, we modify the conditions. That if you have a graph in vertices, 4 vertices,
Okay.
its matrix will be of size 4 by 4. And then 1 entry will be 0.
Okay.
Because we can't have a disjoint path from that vertex to that vertex.
Right.
1, 2 energy degree will be, that means entry will be 1 vertex, 2 vertex, you calculate the paths, vertex disjoint, write that. For every pair, you write the entries, you will be getting n by n matrix. And linear algebra says that if you have a matrix of size n, its polynomial is of degree n. Fundamental theorem says that it has n roots. So it has n eigenvalue. My first example, you know that. First example was saying, I draw the graph, 7 vertices. I wrote its path eigenvalues. I wrote its ordinary eigenvalues. Yes. Now you will say that what is the special property of this eigenvalue? That is different thing. That's why so many people are working on this. So many people, we don't know, you don't think of, we never thought that these people are right. But some people are all the trying to find out new. So 32 papers is not easy. We introduced the idea, we left it. Other people caught the idea and they are doing a lot of things with that. So it is nothing. It is, we are associating new graph to the given graph. Now I will say that your graph is same. So you write adjacency matrix for that. You write path matrix for that. You write CG for that. Last time. You write distance matrix for that. You write path Laplace. You look at that. Matrix will name. You are getting the graph.
So virtually your path energy is
There is an organization from the organizer. I am instructed that I should stop now. So thank you very much. If you have, we can discuss later on.
Sir, we thank Shikara sir for the wonderful talk and the discussions. We'll break for